Welcome to this peaceful journey through the world of .NET. Let yourself relax as we explore these gentle technical concepts. There's no need to memorize anything. Just let the information wash over you like a calm stream. Fact number 1. The evolution of .NET from Windows-only to fully cross-platform and open source. Let's drift back to the year 2002. Microsoft released the first version of the .NET framework, and it was built exclusively for Windows. For over a decade, .NET remained tightly bound to the Windows operating system, living only in that ecosystem. Developers who wanted to build .NET applications needed Windows machines. Servers running .NET applications needed Windows Server. It was a closed world, peaceful in its own way but limited. Then slowly things began to change. Microsoft started to see the value in reaching beyond Windows. In 2014, they announced that .NET would become open source. The code that had been private, held close, would now be shared with the world. And not just open source, but cross-platform too. Developers could now run .NET on Linux, on macOS, on any system they chose. The walls came down gently, gradually. This transformation didn't happen overnight. It took years of careful work, of rewriting, of redesigning. But by the time .NET Core emerged, and later became simply .NET 5, 6, 7, and beyond, the platform had truly become universal. Today, you can write a .NET application on a Mac, deploy it to a Linux server, and know it will run exactly as intended. The journey from closed to open, from limited to universal, represents one of the most significant shifts in the platform's history. Rest easy knowing that .NET now belongs to everyone. Fact number 2. The Common Language Infrastructure, or CLI, as the standardized execution model. Beneath the surface of .NET lies something called the Common Language Infrastructure. It's a specification, a set of rules, a standard that describes how code should be executed. Think of it as a blueprint carefully designed and internationally recognized. The CLI was standardized by ECMA and ISO, which means it's not just a Microsoft invention anymore, but an international standard that anyone can implement. This standard describes how programs should be compiled into an intermediate language, how that language should be executed, how types should work, how memory should be managed. What makes the CLI so peaceful, so reliable, is its universality. When you write code that follows the CLI specification, you know it will work consistently across different implementations. The rules are clear, documented, unchanging. Microsoft's implementation is just one possibility. Mono, another implementation, has existed for years. The CLI is the foundation, the bedrock, the unchanging ground beneath your feet. Let yourself relax into the knowledge that standards like the CLI exist. They bring order to complexity. They ensure that chaos doesn't reign. The CLI quietly does its work, defining how everything should behave, and you can trust it completely. Fact number 3. The CLR as a managed runtime handling memory, JIT, safety, and execution. Now let's talk about the Common Language Runtime, the CLR. This is the engine, the heart of .NET. While you write code, while you think about business logic and user interfaces, the CLR works tirelessly in the background, managing all the difficult details. Memory management, the CLR handles it. You don't need to manually allocate and free memory like in older languages. The garbage collector watches, waits, and automatically cleans up memory you're no longer using. It's like having someone who quietly tidies your room while you sleep, making sure everything stays organized without you lifting a finger. Just-in-time compilation, or JIT. The CLR does this too. Your code is compiled into an intermediate language first, and then, at runtime, the JIT compiler converts it into native machine code specific to your processor. This happens transparently, efficiently, in the background. You never see it, but it ensures your code runs as fast as possible on whatever hardware you're using. Safety and type checking. The CLR provides this as well. It verifies that your code isn't doing anything dangerous, isn't accessing memory it shouldn't, isn't violating type safety rules. It's a guardian, a protector, ensuring that your application stays stable and secure. And execution. The CLR manages the actual running of your code, scheduling threads, handling exceptions, coordinating all the moving parts. It's the conductor of an orchestra, making sure every instrument plays at the right time, in harmony. With the CLR managing everything, you can rest easy. The complex work is handled for you. Fact number 4. How .NET code runs on different operating systems and CPU architectures unchanged. Here's something truly remarkable, something almost magical when you stop to think about it. You can write .NET code once, just once, and it will run on Windows, on Linux, on macOS. It will run on x86 processors, on ARM processors, on different architectures entirely. The code itself doesn't change. You don't rewrite it. You don't modify it. It simply works. This is possible because of that intermediate language we mentioned. Your C# code or F# code or whatever language you choose gets compiled not into machine code specific to one processor, but into something called Common Intermediate Language or CIL. This intermediate language is platform agnostic, neutral, universal. When your application runs, the runtime on that specific platform takes this intermediate language and compiles it into the native machine code for that system. A Linux machine compiles it one way. A Windows machine compiles it another way. An ARM processor gets ARM instructions. An x86 processor gets x86 instructions. But you, the developer, don't worry about any of this. This abstraction, this layer of separation between your code and the hardware, is what makes .NET so portable, so flexible. Write once, run anywhere. It's not just a slogan, it's reality. Your code travels effortlessly across platforms, adapting to each environment while remaining fundamentally the same. There's something deeply peaceful about this universality, this consistency. No matter where your code ends up, it will feel at home. Fact number 5. Multiple languages, C#, F#, VB.NET, sharing one runtime and ecosystem. .NET is not just one language. It's a home for many languages, each with its own personality, its own strengths, its own way of expressing ideas. C# is the most popular, known for its balance of power and simplicity. F# embraces functional programming, treating functions as first-class citizens, emphasizing immutability and expressiveness. VB.NET carries forward the legacy of Visual Basic, with syntax that some find more readable, more natural. But here's what makes .NET special. All these languages share the same runtime, the same libraries, the same ecosystem. They all compile down to that same intermediate language. A library written in C# can be used seamlessly from F# code. An F# function can be called from VB.NET. They interoperate perfectly, effortlessly. This means you can choose the language that fits your problem best, or the language your team knows best, or the language you simply enjoy most, and you still have access to the entire .NET ecosystem. Every library, every tool, every framework works with every language. There's no fragmentation, no walled gardens. Imagine a community where everyone speaks different languages but understands each other perfectly. That's .NET. The diversity of languages enriches the platform, bringing different perspectives, different approaches to solving problems. And yet unity remains. One runtime, one ecosystem, many voices. Let that harmony lull you into peaceful contemplation. Fact number 6. Side-by-side runtime versions enabling safe upgrades. Change can be stressful. Upgrading software can be risky. What if something breaks? What if the new version isn't compatible with the old? .NET understands these concerns and provides a gentle solution. Side-by-side runtime versions. This means you can have multiple versions of .NET installed on the same machine, running simultaneously without conflict. An old application can continue using .NET 6, while a new application uses .NET 8. They coexist peacefully, each running with the runtime version it was designed for. When you're ready to upgrade an application, you can do so on your own timeline. There's no pressure, no forcing you to migrate everything at once. You can upgrade one application, test it thoroughly, make sure everything works, and then move on to the next. The old version remains available, a safety net, a fallback if anything goes wrong. This side-by-side capability extends to libraries and dependencies as well. Different applications can reference different versions of the same library without interfering with each other. It's like having separate rooms in a house, each decorated according to its occupants' preferences, but all existing under the same roof. This design choice reflects a deep respect for stability, for caution, for the reality that enterprises can't drop everything to chase the latest version. Provides peace of mind. You can move forward when you're ready, not when you're forced. The old and the new can coexist harmoniously until you decide it's time to let go of the past. Fact number 7. Compatibility guarantees that protect long-lived enterprise apps. Some applications live for decades. They're built once and maintained for years, handling critical business processes, storing important data, serving thousands or millions of users. These applications can't afford to break when the platform they're built on evolves. .NET recognizes this responsibility and makes strong compatibility guarantees. When a new version of .NET is released, Microsoft works hard to ensure that existing applications continue to work without modification. Breaking changes are rare and carefully considered. When they do occur, they're documented thoroughly, and migration paths are provided. This commitment to compatibility means that an application built on .NET several years ago can often run on the latest .NET version with little or no changes. The foundation remains stable even as new features are added on top. It's like living in a house that gets renovated over the years, new rooms added, new paint applied. But the foundation stays solid, the structure stays sound. For enterprise developers, this is invaluable. They can invest in .NET knowing that their investment won't be wasted, that their applications won't become obsolete overnight. There's a trust here, a promise kept between platform and developer. Your code will be respected. Your work will be protected. Let yourself feel the security of this guarantee. In a world where technology changes rapidly, where today's innovation becomes tomorrow's legacy, .NET provides continuity. Your applications can age gracefully, maintained and updated, but never abandoned, never broken. That's a rare and precious thing. Fact number 8. Modern .NET component model, runtime, libraries, SDK, app stacks. Modern .NET is organized into clear, logical components. Understanding this structure brings clarity, brings peace. There's the runtime, which we've discussed, the engine that executes your code. Then there are the base class libraries, vast collections of pre-written code that handle common tasks. Need to work with files? There's a library. Need to make HTTP requests? There's a library. These libraries save countless hours of work. The SDK, or Software Development Kit, provides the tools you need to build applications. Compilers, command line tools, project templates, everything a developer needs to go from idea to working application. The SDK is your workshop, equipped with every tool you might need. And finally, there are the app stacks, higher-level frameworks built on top of the runtime and libraries. ASP.NET Core for web applications, .NET MAUI for mobile and desktop apps, Blazor for web UIs with C#. Each stack is specialized, optimized for its purpose, but all share the same foundation. This layered architecture is elegant. Each layer builds on the one below it. Each layer can be understood independently. You can work at whatever level suits your needs, low-level runtime details if you're building a framework, or high-level app stacks if you're building business applications. The choice is yours, and every level is well-designed, well-documented, well-supported. Think of it as a mountain with clearly marked trails. You can hike at the base where the terrain is gentle and the path is clear. Or you can climb higher, reaching more specialized, more challenging areas. But wherever you are, you're on the same mountain, supported by the same solid ground. Rest in the knowledge that this structure makes sense, that it's been thoughtfully designed. Fact number 9. Multiple app models, web, desktop, mobile, cloud, workers. .NET doesn't force you into one type of application. It welcomes diversity, embraces different needs, different contexts. Want to build a website? ASP.NET Core is there for you, powerful and flexible. Need a desktop application? Windows Presentation Foundation, or WPF, provides rich UI capabilities. Want cross-platform desktop? There's Avalonia and .NET MAUI. Mobile applications? .NET MAUI lets you build for iOS and Android from a single codebase. Cloud applications? Azure Functions and other serverless options let you build scalable, event-driven systems. Background workers and services? The worker service template provides a foundation for long-running processes. Each of these application models has its own characteristics, its own best practices, its own ecosystem, but they all use the same language, the same runtime, the same core libraries. Skills transfer from one model to another. A web developer can become a mobile developer without learning an entirely new platform. A desktop developer can move to the cloud and feel at home. This versatility means .NET grows with you. As your career evolves, as your projects change, as technology shifts, .NET remains relevant. You're not locked into one type of development. The platform adapts to your needs, rather than forcing you to adapt to its limitations. Imagine a single tool that can build anything: a house, a bridge, a sculpture, a machine. That's what .NET aspires to be. Not perfectly, not without limitations, but with remarkable breadth. Whatever you need to build, .NET probably provides a way. And that's comforting. That's reassuring. You can rest knowing the platform is ready for whatever comes next. Fact number 10. Generic host as the unifying application foundation. Finally, let's talk about the generic host. This might sound technical, but it's actually quite simple and quite beautiful. The generic host is a pattern, a foundation that many different types of .NET applications can build upon. It provides consistent ways to handle configuration, logging, dependency injection, and application lifetime. Whether you're building a web application, a background worker, or a console application, you can use the generic host as your starting point. This means these different application types share common patterns, common approaches. Once you understand how to configure a web application, you understand how to configure a worker service. The knowledge transfers. The generic host brings order. It establishes conventions, provides structure without being rigid. You can customize and extend it, but the foundation remains consistent. This consistency reduces cognitive load. You don't need to learn completely different patterns for each type of application. It's like having a standard foundation for buildings. Whether you're constructing a house, an office, or a store, certain fundamental elements remain the same: plumbing, electrical, structural support. The generic host provides those fundamental elements for .NET applications. Build on it, and you start from a position of strength, of proven patterns, of best practices. As we close this first segment, let yourself absorb these ideas. The evolution from closed to open, the standardization of execution, the managed runtime taking care of complexity, the portability across platforms, the harmony of multiple languages, the safety of side-by-side versions, the promise of compatibility, the clarity of modern architecture, the versatility of application models, the consistency of the generic host. These are the foundations of .NET. These are the principles that make it powerful yet approachable, complex yet manageable. Rest easy in this knowledge. Let it settle into your mind as you drift towards sleep. The world of .NET is vast, but it's also carefully designed, thoughtfully structured, built to support you. Sleep well. And now we continue our gentle journey deeper into the world of .NET. Let your breathing slow, let your mind drift, as we explore the next layer of understanding. Fact number 11. IL, Intermediate Language and CPU-Agnostic Compilation. When you write code in C# or F#, your compiler doesn't immediately convert it into instructions that your processor understands. Instead, it takes a middle step, a peaceful pause between source and execution. Your code becomes intermediate language, sometimes called IL, sometimes called CIL for Common Intermediate Language, or even MSIL, Microsoft Intermediate Language. These names all refer to the same thing, a neutral representation of your code. This intermediate language sits between worlds. It's not source code anymore, but it's not machine code either. It's abstract, platform neutral, CPU agnostic. An IL instruction might say, add these two numbers or call this method, but it doesn't specify exactly how the processor should do these things. Those details come later. Think of IL as a universal language, understood by all .NET runtimes but tied to none. A book written in this language can be read anywhere, by anyone, regardless of what kind of computer they're using. This is why your .NET assembly, that DLL or exe file, can move from one machine to another so effortlessly. JIT carries IL with it, and wherever it goes, the local runtime knows how to read it, how to understand it, how to execute it. This abstraction is what makes portability possible. You compile once to IL, and that IL can run anywhere .NET exists. The hard work of making it run on specific hardware happens later, happens automatically, happens without you needing to think about it. Let yourself appreciate the elegance of this design. Your code exists in a pure, portable form, ready to adapt to whatever environment it encounters. There's something deeply peaceful about this flexibility, this readiness. Fact number 12. JIT compilation and environment-specific optimizations. Now let's talk about what happens when your IL actually runs. This is where the just-in-time compiler, the JIT, enters the picture. As your application starts, as methods are called for the first time, the JIT compiler watches and waits. When it's time to execute a method, the JIT springs into action. It takes the IL for that method and compiles it into native machine code, the actual instructions your processor understands. But here's what makes the JIT special. It doesn't just blindly translate. It looks at the environment. What kind of processor is this? Does it support special instruction sets? How much memory is available? What optimizations make sense here? The JIT adapts. On a modern processor with advanced vector instructions, the JIT might use those. On an older processor, it generates simpler code. On a machine with lots of memory, it might make different trade-offs than on a constrained device. This compilation happens right there, in the moment, with full knowledge of the actual hardware that will run the code. And it's just in time. Not too early, that would waste work on code that never runs. Not too late, that would delay execution when you need it. Right when it's needed, the JIT compiles and the compiled code stays in memory, ready for the next time that method is called. The first call pays the compilation cost. Subsequent calls run at full native speed. This is optimization without effort on your part. You don't need to compile different versions for different processors. You don't need to detect capabilities and branch your code. The JIT handles it all silently, efficiently, adapting your code to its environment like water conforming to its container. Rest in the knowledge that your code will always run as well as possible wherever it runs. Fact number 13. Tiered compilation balancing startup versus throughput. Here's an interesting challenge. The JIT compiler can produce really fast code, but producing that fast code takes time. If the JIT spends too long optimizing, your application starts slowly. But if it doesn't optimize enough, your application runs slowly. How do you balance these competing needs? The answer is tiered compilation. Think of it as a gradual process, a patient approach. When a method is first called, the JIT compiles it quickly with minimal optimization. This tier 0 code is fast to compile but not particularly fast to run. The goal is just to get your application started, to make progress, to avoid that frustrating pause when you launch a program. But the runtime watches. It tracks which methods are called frequently, which methods are hot, which methods would benefit from deeper optimization. And for those methods, after they've been called several times, the JIT recompiles them. This time, it invests more effort. This tier 1 code is heavily optimized, inlined, vectorized, branch predicted, all the techniques that make code truly fast. So you get the best of both worlds. Fast startup because initial compilation is quick, and high throughput because frequently used code eventually gets fully optimized. The runtime learns from your application's behavior and adapts its compilation strategy accordingly. This happens automatically. You don't configure it. You don't manage it. The runtime observes, decides, and acts. It's like having an assistant who learns your habits and optimizes your workflow without being asked. Your application starts quickly in the morning and runs smoothly throughout the day. The balance is maintained. The trade-off is resolved. Let this knowledge ease any concerns about performance. The system knows what it's doing. Fact number 14. Profile-guided optimization, adapting code to real workloads. Even deeper than tiered compilation is profile-guided optimization, or PGO. This is where the runtime doesn't just count how many times a method is called, but pays attention to what actually happens inside the method. Which branches are taken most often? Which types are actually used in generic code? Which interface calls go to which implementations? With this detailed information, the runtime can make incredibly smart decisions. If a branch is almost always true, the JIT can arrange the machine code so that the common path is fastest. If a generic method always receives integers, the JIT can specialize the code for integers. If an interface call always goes to the same concrete class, the JIT can potentially devirtualize the call, making it much faster. This is optimization based on reality, not guesses. The runtime watches your actual workload, your actual data, your actual usage patterns, and tailors the compiled code to match. It's deeply personal, in a way. Your application's compiled code becomes unique to how you use it, shaped by the specific patterns and behaviors of your workload. And this happens dynamically at runtime. The runtime keeps learning, keeps refining. If your workload changes, if different code paths become hot, the runtime adapts. It's never static, never frozen. It's alive, responsive, always working to make your application faster. Imagine a path through a forest that slowly becomes more defined as more people walk it. The most traveled routes become clearer, smoother, easier to follow. That's what PGO does to your code. The most traveled code paths become optimized, refined, perfected. Let yourself trust in this process. Your application is always being improved, always being fine-tuned, always learning. Rest easy knowing that performance is not something you have to fight for. The runtime is on your side, working for you even while you sleep. Fact number 15. Ready to run images for faster cold starts. Sometimes, even the fastest JIT compilation isn't fast enough. When you start an application, you want it to respond immediately. You don't want to wait while the JIT compiles method after method. This is especially important for applications that start frequently, command line tools, serverless functions, apps that launch on demand. Ready to Run, or R2R, offers a solution. When you publish your application, you can include ahead-of-time compiled native code alongside the IL. This native code is ready to run immediately, no JIT compilation needed. When your application starts, the methods with R2R code can execute right away. But here's the clever part. The IL is still there. If the runtime encounters a situation where the R2R code isn't optimal, maybe the R2R code was compiled for a generic processor but you're running on one with better capabilities, it can fall back to JIT compilation and generate better code. R2R provides a good enough starting point, and JIT provides the eventually optimal code. This hybrid approach gives you fast startup without sacrificing runtime performance. It's the best of both worlds again. Another balance, another thoughtful compromise. Your application launches quickly, and if it runs long enough, it gets even faster as the JIT recompiles hot methods. R2R images are larger than pure IL assemblies because they contain both the native code and the IL. But that's okay. Disk space is cheap and startup time is precious. The trade-off makes sense. When you enable Ready to Run, you're choosing to pay a little more in size to gain a lot in responsiveness. Think of R2R as a pre-warmed engine. When you start your car on a cold morning, you want it ready to go. Ready to Run provides that immediate readiness, that instant response. Your users don't wait. Your application feels snappy, alive, eager. And underneath, the JIT is still there, still watching, still ready to optimize further if needed. Everything works together harmoniously. Fact number 16. Native AOD for fully compiled native binaries. But what if you want to go further? What if you want to eliminate the JIT entirely, compile everything ahead of time, create a single native executable with no runtime dependencies? This is what native AOD ahead-of-time compilation provides. With native AOD, your .NET application is compiled into a native binary, just like a C or C++ program. There's no IL at runtime. There's no JIT compilation. It's just native machine code, ready to execute. This brings several benefits. Incredibly fast startup, minimal memory usage, and small deployment size because you don't need to include the JIT compiler or other runtime components that aren't strictly necessary. Native AOD is perfect for certain scenarios. Microservices that need to start in milliseconds. Command line tools that should be instant. Embedded systems with constrained resources. Environments where you can't have a JIT for security or policy reasons. In these cases, native AOD shines. But there are trade-offs, as always. Some .NET features that depend on runtime code generation won't work or require special handling. Reflection becomes more complicated. The compilation process is slower, and the optimizations are fixed at compile time rather than adapting to the actual runtime environment. Still, for the right scenarios, native AOT is powerful. It's .NET meeting traditional native applications on their own terms. It's proof that .NET can be tiny, fast, and self-contained when needed. You have the choice. You can embrace the dynamic, adaptive nature of JIT compilation, or you can choose the predictability and minimalism of native AOT. The platform supports both philosophies. Let this flexibility wash over you. .NET doesn't force you down one path. It provides options, alternatives, different tools for different needs. You remain in control, able to choose the approach that fits your situation. That's the sign of a mature, thoughtful platform. Fact number 17. Trimming and minimal publishing for small deployments. Related to native AOT is the concept of trimming. When you publish a .NET application normally, you get all the libraries, even the parts you don't use. This is safe and simple, but it makes your deployment larger than necessary. Trimming analyzes your code and removes the parts that aren't reachable, aren't used, aren't needed. The trimmer starts from your application's entry point and traces through all the code paths. It marks every method, every class, every assembly that's actually used. And then it removes everything else. What remains is a minimal set of code, just enough to run your application and nothing more. This can dramatically reduce deployment size. A full .NET application with all libraries might be tens or hundreds of megabytes. A trimmed application might be just a few megabytes. For deployments to edge devices, for container images that need to be downloaded quickly, for any scenario where size matters, trimming is invaluable. But trimming requires care. If your code uses reflection to dynamically access types or methods, the trimmer might not see those usages and might remove code you actually need. You have to be aware of this, have to configure the trimmer correctly, have to test thoroughly. It's powerful but not entirely automatic. Combined with native AOT and single-file publishing, trimming can produce incredibly compact deployments. Your entire application, self-contained, native, ready to run, in just a few megabytes. From the sprawling hundreds of megabytes of the full .NET runtime to a lean, focused executable containing only what's necessary. It's like packing for a trip and taking only what you truly need, leaving everything else behind. This minimalism is elegant. There's a zen quality to it, removing the unnecessary, keeping only the essential. Your deployment becomes lighter, faster, more efficient. And in a world of constrained resources and slow networks, that matters. Rest in the knowledge that .NET can be as large or as small as you need it to be. Fact number 18. Code verification and type safety enforcement. Let's talk about safety, about protection, about the guardrails that keep your application stable. When IL is loaded into the runtime, before it ever executes, the runtime verifies it. This verification checks that the IL is well-formed, that it doesn't try to do anything dangerous, that it respects type safety rules. Type safety means that the code doesn't treat an integer as a pointer, doesn't access an array out of bounds, doesn't call methods on objects of the wrong type. These kinds of errors cause crashes in unmanaged languages like C or C++. In .NET, the verifier catches them before they cause harm. This verification happens at the IL level before JIT compilation. If the IL doesn't verify, the runtime refuses to execute it. This is a hard boundary, a protective wall. Only safe code runs. Only code that respects the rules, that doesn't violate type safety, that doesn't attempt memory corruption, is allowed to execute. This makes .NET applications more stable, more secure. Entire categories of vulnerabilities, buffer overflows, type confusion, use after free, are prevented by the runtime's verification process. You can't accidentally corrupt memory. You can't accidentally create a security hole through unsafe pointer arithmetic. The runtime simply won't let you. Of course, there are escape hatches. You can write unsafe code if you need to, for performance or interoperability reasons. But you have to explicitly mark it as unsafe, and it requires special permissions to run. The default is safety. The default is protection. You have to consciously step outside those boundaries. Imagine living in a house where dangerous tools are locked away, where sharp edges are padded, where hazards are eliminated. You can still access those tools if you need them, but you have to deliberately unlock the cabinet. That's what verification provides. A safe environment by default, with expert-level capabilities available when needed. Sleep peacefully knowing the runtime is watching, protecting, ensuring your code behaves correctly. Fact number 19. Assemblies as self-describing deployment units. An assembly is the fundamental unit of deployment in .NET. It's a DLL or exe file, but it's more than just code. It's self-describing, meaning it contains metadata about itself, what types are defined within it, what methods exist, what dependencies it has, what version it is. This metadata is crucial. When the runtime loads an assembly, it reads this metadata to understand what's inside. No separate header files, no external configuration, no guesswork. Everything needed to use the assembly is contained within the assembly itself. It's complete, self-sufficient, autonomous. This self-describing nature makes deployment simpler. You copy an assembly, and all the information needed to use it comes along. Tools can inspect assemblies without needing source code. Debuggers know what types and methods exist. The runtime knows what dependencies need to be loaded. Everything is discoverable, queryable, introspectable. Assemblies also define a boundary for versioning and security. Each assembly has a version number. Each assembly can be signed. Each assembly is a distinct, manageable unit. You can update one assembly without touching others. You can have multiple versions of the same assembly side by side. The assembly is the atom, the indivisible unit of .NET deployment. Think of an assembly as a book that includes its own table of contents, its own index, its own description of what it contains. You don't need to consult external resources to understand it. You just open it and read the metadata. This self-sufficiency, this completeness makes assemblies easy to work with, easy to manage, easy to reason about. They're well-behaved citizens of the .NET ecosystem. Fact number 20. Strong names, versioning, and dependency resolution. Finally, let's talk about how .NET manages the complex web of dependencies between assemblies. When your application uses a library, which uses another library, which uses yet another library, how does the runtime keep track? How does it ensure you get the right versions? How does it prevent conflicts? Strong names are part of the answer. An assembly can be signed with a cryptographic key, giving it a strong name that includes not just the assembly's name but also its version number and public key token. This creates a unique identity. My library version 1.0 signed with key A is definitively different from my library version 2.0 or my library version 1.0 signed with key B. With strong names, the runtime can be precise about dependencies. Your application can say, I need exactly this version of this library, signed by this publisher. The runtime respects these requirements, loading the correct assembly and preventing version conflicts. Versioning is careful and deliberate. Each assembly has a 4-part version number: major, minor, build, and revision. Changes to the major version signal breaking changes. Changes to minor version signal new features. Changes to build and revision signal bug fixes or minor updates. This semantic versioning helps everyone understand what kind of change they're dealing with. Dependency resolution is the runtime's job. When your application starts, the runtime examines the dependency graph, figures out which assemblies are needed, and loads them. It handles version binding redirects, probing paths, and the global assembly cache. This complex machinery working behind the scenes, but from your perspective, things just work. The right assemblies are loaded. Dependencies are satisfied. The application runs. Imagine a librarian who knows every book in the library, knows which books reference which other books, and can instantly pull the right edition of any book you need. That's what .NET's dependency resolution system does. It manages complexity so you don't have to. It ensures that all the pieces fit together correctly, that every dependency is satisfied, that nothing is missing or mismatched. As we close this second segment, let these concepts settle into your mind. The portability of intermediate language, the adaptability of JIT compilation, the balance of tiered compilation and PGO. the speed of ready-to-run and native AOD, the minimalism of trimming, the safety of verification, the completeness of assemblies, the precision of strong naming and dependency resolution. These are the mechanisms that make .NET work, the gears and springs of the platform. They operate quietly, reliably, doing their job without fanfare. You write code, and these systems ensure it runs safely, quickly, correctly. You deploy applications, and these systems ensure dependencies are satisfied, versions are respected, conflicts are avoided. Rest easy. The platform handles so much for you. Trust in these systems. Let them support your work as you drift deeper into peaceful sleep. The foundation is solid. The mechanisms are sound. All is well in the world of .NET. Now we drift into the realm of memory, of resources, of how .NET manages the finite space where your data lives. Let your thoughts settle as we explore these gentle concepts. Fact number 21. Generational, compacting garbage collector. Memory is precious. Objects are created, used, and eventually no longer needed. In languages like C, you must manually track every allocation and remember to free it. Forget, and you have a memory leak. Free too early, and you have a crash. It's exhausting, error-prone, a constant source of worry. .NET relieves you of this burden with automatic garbage collection. The garbage collector, or GC, watches over your memory. It tracks which objects are still reachable, still in use, and which have become orphaned, unreachable, ready to be reclaimed. And when memory pressure builds, the GC runs, cleaning up, making space for new objects. But the GC is clever. It divides objects into generations, Generation 0, Generation 1, and Generation 2. New objects start in Generation 0. This is where most objects live and die quickly. A temporary variable, a string built during a calculation, an object created to process one request. These live briefly and are collected quickly. Objects that survive a collection are promoted to Generation 1. If they survive again, they move to Generation 2. These are the long-lived objects, the stable residents of your application's memory. The GC checks Generation 0 frequently but checks Generation 2 rarely. This is efficient because most objects die young. Why waste time scanning long-lived objects that are almost certainly still needed? The GC is also compacting. After collecting dead objects, it moves the surviving objects together, eliminating gaps, keeping memory tidy and contiguous. This prevents fragmentation, keeps allocations fast, maintains order. It's like tidying a bookshelf, pushing all the books together so there's room for more. Let yourself relax into the knowledge that memory is being managed for you. You create objects freely, use them as needed, and let them go without worry. The garbage collector watches, waits, and quietly cleans up. It's gentle, efficient, thoughtful. You don't need to think about deallocation. You can focus on your logic, your algorithms, your application's purpose. The GC handles the rest. Fact number 22. Workstation versus server GC modes. Not all applications have the same needs. A desktop application wants to stay responsive, to not freeze the UI during garbage collection. A server processing hundreds of requests per second wants maximum throughput, even if individual pauses are slightly longer. The garbage collector adapts to these different scenarios with two modes: Workstation GC and Server GC. Workstation GC is optimized for latency, for quick pauses, for keeping the application responsive. It uses a single thread for garbage collection, minimizing overhead. Collections happen more frequently but complete quickly. The user never notices. The application stays smooth and fluid. Server GC is optimized for throughput, for handling large workloads efficiently. It uses multiple threads for garbage collection, one per logical processor. It collects larger heaps in parallel, using all available CPU cores. Individual pauses might be longer, but overall throughput is higher. More work gets done. The runtime chooses the appropriate mode automatically based on your application type, but you can override this if needed. A web server typically uses Server GC. A GUI application uses Workstation GC. The choice aligns with the workload, with the priorities, with the context. This flexibility is reassuring. The garbage collector doesn't enforce one strategy for all situations. It recognizes that different applications have different needs and provides the right tool for each job. Whether you need responsiveness or throughput, the GC can deliver. It's adaptable, configurable, thoughtful. Imagine a gardener who adjusts their techniques based on the season, the plants, the weather. Sometimes they water frequently in small amounts. Sometimes they water deeply but less often. The GC is like this, adjusting its strategy to fit the environment, always working toward healthy growth, sustainable resource usage. Rest knowing the GC is working in harmony with your application's needs. Fact number 23. Why short-lived objects are optimized. Here's a fundamental observation about most programs. Objects tend to die young. You create a string during a calculation, it's used once, and then it's no longer needed. You allocate an array to hold temporary results, process them, and move on. You construct objects to pass data between methods, and once that call completes, those objects become garbage. The .NET garbage collector is built around this observation, this generational hypothesis. Generation 0 collections are fast, incredibly fast. Allocating objects in Generation 0 is fast too, often just a pointer bump. The entire design assumes that most objects will live briefly and optimizes for that common case. This means you can create objects freely without guilt. Need a temporary list? Create it. Need to build a string? Create intermediate strings without worry. The cost of these short-lived allocations is minimal. They'll be collected quickly, efficiently, with minimal overhead. This is liberating. In other languages, you might hesitate before allocating memory, might try to reuse objects, might contort your code to minimize allocations. In .NET, especially for short-lived objects, allocation is cheap. The GC is on your side, designed to handle exactly this pattern. There's something peaceful about this alignment between programming patterns and runtime optimization. The natural way to write code, creating objects as needed, letting them go when done, is also the efficient way. You don't fight the platform. You work with it. The GC's optimization of short-lived objects makes idiomatic .NET code also performant .NET code. Let this sink in. You don't need to hoard and reuse every object. You don't need to optimize prematurely. Write clear code, create objects when they make sense, and trust the GC to handle the short-lived ones efficiently. It's designed for this. It excels at this. Your natural coding style is already optimized. Fact number 24. Stack allocation with Stackalok. While the heap and garbage collector handle most memory, there's another option for specific scenarios, the stack. The stack is fast. Allocation is just moving a pointer. Deallocation happens automatically when a method returns. But the stack is limited in size and scope. Stack memory is tied to a method's execution. For small, temporary buffers, the Stackalok keyword lets you allocate memory on the stack instead of the heap. This bypasses the garbage collector entirely. You get raw memory fast with automatic cleanup when the method exits. For performance-critical code that needs small buffers, Stackalok is powerful. But Stackalok comes with constraints. The memory must be small, too large, and you risk stack overflow. The memory only lives as long as the method. You can't return it or store it in long-lived objects. And you must be careful about safety, about not writing past the buffer's bounds. Modern .NET makes Stackalok safer by combining it with span-t, which we'll discuss soon. This combination gives you stack performance with safety guarantees. You get the best of both worlds, speed and protection. Stack allocation is like using a notepad on your desk for quick calculations. The notepad is always there, always ready, and you erase it when done. For temporary work, it's perfect. For long-term storage, you need something else. Stackalok serves this same purpose: quick, temporary memory for small, performance-critical scenarios. The existence of Stackalok shows .NET's pragmatism. While garbage collection handles most needs, the platform recognizes that sometimes you need lower-level control, sometimes you need to optimize specific hot paths. And so the tools are there, available when needed but not required for everyday coding. Rest in this flexibility, this recognition that different problems need different solutions. Fact number 25. Spanned T and memory Teak 4 zero allocation slicing. One of the most elegant additions to modern .NET is spanned Teak. A span is a view over contiguous memory, an array, part of an array, stack memory, even unmanaged memory. It's type-safe, bounds-checked, and incredibly fast. And most importantly, creating a span doesn't allocate memory. Imagine you have a large array and want to work with just a portion of it. In the past, you might copy that portion into a new array. That's an allocation, that's copying data, that's work for the garbage collector. With spanned T, you create a lightweight view. No copying, no allocation, just a pointer and a length. You can slice the span further, creating views of views, all without allocating. Spanned T lives on the stack, so it has some restrictions. You can't store it in a field or use it in async methods. For those scenarios, there's memory T, which is similar but can live on the heap. Memory T can be stored, can be used with async, but when you actually need to work with the data, you get a spanned T from it. These types enable zero allocation algorithms. You can parse strings without creating substrings. You can process buffers without copying data. You can work with memory efficiently, with safety, with elegance. Many .NET APIs have been updated to accept spans, making this efficiency widely available. Think of spanned T as a window. You're not moving the house to see a different view, you're just repositioning the window. The house stays where it is. The data stays where it is. You just change what you're looking at. This metaphor captures the lightness, the zero-cost nature of spans. Spanned T represents modern .NET's commitment to performance without sacrificing safety. You get C++ level efficiency with C# level protection. You can write high-performance code that's still verifiable, still safe, still maintainable. Let yourself appreciate this achievement. The platform grows more capable while remaining approachable. Fact number 26. Implicit spans in modern APIs. Spanned T is powerful, but it becomes even better when you don't have to think about it. Modern .NET APIs increasingly accept spans implicitly. You might pass a string and it's treated as a span of characters. You might pass an array, and it's seen as a span of elements. The conversion happens automatically, seamlessly. This means you get the benefits of spans without changing your code. Libraries that accept read-only span char for string parsing can still be called with regular strings. You're not forced to learn new patterns or rewrite existing code. The optimization happens under the hood. This is good API design, providing flexibility and performance while maintaining simplicity. The advanced user can pass precisely sliced spans for maximum efficiency. The casual user can pass arrays or strings and still benefit. Everyone wins. Over time, as .NET has evolved, more and more APIs have adopted span-based signatures. String manipulation, encoding, parsing, serialization, all these areas now support spans. The ecosystem is gradually becoming more allocation-free, more efficient, more performance-conscious. And you benefit from these improvements even if you're not explicitly using spans yourself. It's like living in a house where the foundation has been reinforced, the insulation upgraded, the efficiency improved, all while the rooms you inhabit look and feel the same. You enjoy the benefits, lower heating bills, better comfort, without needing to understand the technical improvements. Modern .NET works this way. Better performance flows through the platform, available to all. Fact number 27. Avoiding boxing and unboxing costs. In .NET, there are value types and reference types. Value types, integers, structs, enums, live directly where they're stored, often on the stack. Reference types, classes, strings, arrays, live on the heap, and you hold a reference to them. This distinction is usually invisible, but sometimes value types need to be treated as objects, as reference types. This process is called boxing. When you box a value type, the runtime allocates space on the heap, copies the value there, and gives you a reference. When you unbox, it copies back. Both operations have cost, allocation, copying, eventual garbage collection. For performance-sensitive code, boxing is something to avoid. Generics largely eliminate the need for boxing. A list int stores integers directly, no boxing needed. Before generics, collections stored objects, and every integer added was boxed. Generics changed this, making collections type-safe and efficient. But boxing can still happen in subtle ways. Calling to string on a value type passed as object boxes it. Using a value type in string interpolation might box it. Being aware of these situations helps you avoid unnecessary overhead. Modern .NET has worked to reduce implicit boxing. APIs that once required objects now often have generic overloads. The platform evolves toward less boxing, less allocation, more efficiency. Your code benefits even if you're not consciously thinking about it. Think of boxing as gift wrapping a small item. The item itself is tiny, but the wrapping, the box, the ribbon, they add bulk and cost. If you're passing the item directly without wrapping, it's simpler, lighter, faster. Value types used directly without boxing are like this, efficient and straightforward. Let the runtime's optimization of generics and modern APIs handle boxing concerns. Trust that the platform is designed to minimize these costs. Fact number 28. Object pooling with array pool, TEAB. Even though allocation is cheap, sometimes you want to avoid it entirely. If you're creating and discarding large arrays repeatedly, even generation 0 collections add up. For these scenarios, object pooling is the answer. Instead of allocating new arrays, you rent them from a pool, use them, and return them. ArrayPool is .NET's built-in pooling mechanism for arrays. You call rent to get an array, use it, and call return. When done, the pool manages a collection of arrays, reusing them across multiple callers. No allocation during the steady state, no work for the garbage collector, just reuse. The returned array might be larger than requested. The pool rounds up to standard sizes. That's okay. You just use the portion you need. And you must remember to return the array. Forgetting creates a slow leak, not a memory leak exactly, since the pool still references the arrays, but a pool exhaustion leak where the pool keeps growing. Modern .NET APIs sometimes use ArrayPool internally, giving you the benefits automatically. SP.NET Core, for instance, uses pooling for various buffers. You might not explicitly call ArrayPool, but you're benefiting from it. Pooling is most valuable for frequently allocated large objects. Small objects are cheap enough that pooling overhead isn't worth it. But for large arrays, especially in hot paths, pooling can significantly reduce GC pressure and improve performance. Imagine a library that lends books instead of selling them. You borrow a book, read it, return it. Someone else borrows the same book later. This reuse is efficient, reducing waste. ArrayPool works the same way, lending arrays, accepting returns, reducing the need for new allocations. It's a pattern of sustainability, of careful resource management. When you need it, it's there, ready to optimize your memory usage. Fact number 29. Lazy TEAB4 deferred, thread-safe initialization. Sometimes you have an expensive object that might not always be needed. Creating it upfront wastes resources, but you need it to be ready when required. Lazy initialization defers creation until first use. The lazy T type makes this easy and thread-safe. You create a lazy T with a factory function that knows how to create the object. No work happens yet. The object isn't created. The function isn't called. Everything waits. Then, when you access the value property for the first time, the function runs, the object is created, and it's cached. Future accesses return the same instance. And this is thread-safe by default. Multiple threads can access the lazy T simultaneously, and only one will create the object. The others will wait and then receive the same instance. No duplicate work, no race conditions, no need for manual locking. This pattern is perfect for singletons, for expensive resources, for objects that might not be needed every time. You get the benefits of late initialization without the complexity of manual synchronization. Lazy T handles the details. It's also memory efficient in a subtle way. If the object is never needed, it's never created. No allocation, no cost. You only pay for what you use. This aligns with the broader .NET philosophy: make the common case cheap, provide optimizations for careful users, waste nothing. Think of lazy T as a seed. The potential for growth exists, but nothing happens until conditions are right. Then, when water and sunlight arrive, when the value property is accessed, growth begins. The plant emerges, and from then on, it's there, established, ready. Lazy initialization is patient, efficient, waiting for the right moment. Let lazy T handle deferred creation. Trust its thread safety. Use it when initialization is expensive and might not be needed. Fact number 30. Weak reference for memory-sensitive caches. Caching is a powerful optimization. Calculate something once, store the result, reuse it. But caches can cause problems. If a cache holds strong references to objects, those objects can never be garbage collected. The cache grows indefinitely, consuming memory, potentially causing out-of-memory errors. Weak reference provides a solution. Instead of holding a strong reference, you hold a weak one. The garbage collector can still collect the object if memory pressure builds. Your cache holds the object if possible, but releases it if necessary. It's a hint, a preference, not a mandate. You create a weak reference to an object. Later, you try to retrieve the object by calling try-get-target. If the object is still alive, you get it back. If it's been collected, you get null, and you know you need to recreate it. The cache becomes memory-sensitive, automatically adapting to available resources. This is perfect for caches where the cache data can be regenerated, images that can be reloaded, parsed data that can be reparsed, computed results that can be recomputed. The cache provides performance when memory is plentiful but doesn't prevent garbage collection when memory is scarce. Weak reference is part of .NET's toolkit for managing memory carefully. It's not needed often, but when you need it, it's invaluable. It's another example of the platform providing advanced tools for specific scenarios while keeping everyday coding simple. Think of a weak reference as a bookmark. You mark a page, but if the book is removed from the shelf, your bookmark can't bring it back. It's a lightweight pointer, a hopeful reference that acknowledges reality. Sometimes resources are reclaimed, and that's okay. The system adapts, recreates when necessary, and continues forward. As we close this third segment, let these memory management concepts settle into your consciousness. The generational garbage collector quietly cleaning up. The workstation and server modes adapting to different needs. The optimization of short-lived objects. The speed of stack allocation. The elegance of spans and zero allocation slicing. The efficiency of avoiding boxing. The reuse of pooled arrays. The deferred initialization of lazy T. The memory sensitivity of weak reference. These are the tools and patterns that make .NET memory efficient without burdening you with manual memory management. The platform handles complexity. You write straightforward code. The garbage collector watches over everything, cleaning, organizing, optimizing. Memory is managed carefully, thoughtfully, automatically. Rest in this knowledge. Let go of concerns about leaks, about fragmentation, about manual deallocation. The runtime handles it. The patterns support you. All is taken care of. Drift deeper into sleep. Secure in the foundation. .NET provides for memory management. The system works tirelessly so you don't have to. And now we enter the realm of performance, of concurrency, of making your applications fast and responsive. Let these concepts flow over you like a gentle stream. Fact number 31. Async/await and asynchronous I/O scalability. Most applications spend time waiting. Waiting for a database to respond. Waiting for a file to be read. Waiting for a network request to complete. During this waiting, the thread sits idle, doing nothing, consuming resources but producing no work. This is wasteful, especially on servers handling many concurrent requests. Asynchronous programming solves this elegantly. When you await an I/O operation, the thread is released back to the thread pool. It can handle other work while the I/O happens in the background. When the operation completes, a thread, perhaps the same one, perhaps a different one, resumes your method right where it left off. No blocking, no wasted threads, just efficient use of resources. The async and await keywords make this beautiful. You write code that looks synchronous, that reads top to bottom, but the compiler transforms it into an efficient state machine. The complexity is hidden. The benefits are automatic. You get scalability without sacrificing readability. This is crucial for web servers. With synchronous I/O, each request needs a dedicated thread while waiting. With async I/O, threads are shared across many requests. A server can handle thousands of concurrent connections with just a handful of threads. The scalability improvement is dramatic. And it's not just servers. Desktop applications benefit too. Using async for I/O keeps the UI responsive. The user never sees a freeze, never experiences that frustrating pause. The application feels fluid, alive, always ready to respond. Let yourself appreciate the elegance of async/await. Complex concurrency patterns become simple. Scalability becomes accessible. Code remains readable while performance improves dramatically. It's one of .NET's greatest achievements, making hard things easy, making efficient code natural to write. Rest in the knowledge that async is there, ready to make your applications more scalable, more responsive, more efficient. Fact number 32. Thread pool integration with async workloads. Behind async/await is the thread pool, a collection of worker threads managed by the runtime. When you await an operation and it completes the continuation, the code after the await is typically scheduled on the thread pool. A thread picks up the work and executes it. The thread pool is smart. It monitors workload and adjusts the number of threads dynamically. If work is piling up, it adds threads. If threads are idle, it retires them. This automatic tuning means you don't manually manage thread creation. The runtime handles it, optimizing for throughput and efficiency. The integration between async and the thread pool is seamless. You don't think about threads explicitly. You write async methods and the runtime coordinates everything, scheduling continuations, balancing workload, ensuring progress. It's orchestration at a grand scale, and it happens automatically. There's also hill climbing, an algorithm the thread pool uses to find the optimal number of threads. Too few threads and work sits idle. Too many threads and context switching overhead dominates. The hill climbing algorithm explores different thread counts, measures throughput, and converges on the optimal number. It's adaptive, responsive, always tuning itself to current conditions. This is infrastructure you don't see but constantly benefit from. Every async method you write, every await you use, relies on this carefully engineered thread pool. It's like the electrical grid. Invisible, reliable, always there when you flip the switch. Trust the thread pool. Let it handle thread management. Focus on your logic, your algorithms, your application's purpose. The runtime handles the rest. Fact number 33. Value task for high-throughput async paths. Async methods usually return task or task T. These are reference types, allocated on the heap. For most scenarios, this is fine, the allocation is small, and tasks are typically awaited once. But in high-performance scenarios where async methods complete synchronously most of the time, even these small allocations add up. Value task and value task T provide an alternative. They're value types, often living on the stack. When an async method completes synchronously, the data is already cached. The operation finishes immediately. Value task avoids allocating a task object. Zero allocation, zero GC pressure, just pure efficiency. But value task comes with rules. It should only be awaited once. It shouldn't be stored or used as a general-purpose task replacement. These constraints are necessary for the optimization to work correctly. In scenarios where these rules are acceptable, like request/response pipelines where each operation is awaited exactly once, value task shines. Many .NET APIs have added value task overloads, especially in high-performance libraries. You get the benefits automatically when calling these APIs. And if you're writing hot async paths, using value task can significantly reduce allocations. This is micro-optimization made accessible. You don't need to understand assembly language or hardware details. You just use value task instead of task in appropriate scenarios, and you get measurable performance improvements. The platform provides the tools. You choose when to use them. Think of value task as a lightweight courier. For quick, local deliveries where the package is already ready, why use a heavy truck? A bicycle is faster, more efficient, perfectly adequate. Value task is that bicycle, lean, fast, appropriate for specific scenarios. When you need it, it's there, ready to optimize your high-throughput async code. Fact number 34. Cancellation token propagation and cooperative cancellation. Sometimes operations need to be canceled. A user closes a window, a request times out, a shutdown is initiated. Canceling running operations gracefully, without leaving resources in inconsistent states, is important. Cancellation token provides the mechanism. You create a cancellation token source and get a cancellation token from it. This token is passed through your async call chain. Methods check the token periodically. Is cancellation requested? If so, they clean up and exit. If not, they continue working. This is cooperative cancellation. The operation isn't forcibly terminated. It's asked to cancel and it decides how to respond. This preserves consistency, allows cleanup, prevents corruption. The operation exits gracefully, releasing resources, completing what it can before stopping. Cancellation tokens propagate naturally through async code. You pass them as parameters and each level of your call stack checks them. When cancellation is requested at the top, all layers respond, unwinding cleanly. It's elegant, composable, reliable. Many .NET APIs accept cancellation token parameters. HTTP requests, database queries, file operations, they all support cancellation. You can wire up cancellation once at the application level, and it flows through your entire async call tree. This consistency makes cancellation easy to implement, easy to reason about. Imagine a group of people working together, where a signal can be sent that it's time to stop. Everyone sees the signal and wraps up their work in an orderly fashion. No one is rudely interrupted. Everyone finishes their current task and exits cleanly. Cancellation token provides this coordinated, respectful shutdown. Let it flow through your async code, providing clean cancellation, graceful termination, orderly cleanup. Fact number 35. Parallel class for CPU-bound loops. While async/await excels at I/O-bound work, CPU-bound work, heavy calculations, image processing, data transformation, benefits from different patterns. The parallel class provides simple ways to parallelize loops across multiple cores. Parallel. For and parallel. For each, take a loop and execute iterations in parallel. The runtime manages thread allocation, load balancing, and coordination. You write what looks like a sequential loop, and it runs in parallel automatically. All your CPU cores are utilized, work completes faster, and you didn't manually spawn threads or manage synchronization. The parallel class is smart about load balancing. If some iterations take longer than others, faster threads pick up more work. Everything stays busy, and throughput is maximized. This dynamic work distribution is crucial for uneven workloads. There are options for controlling parallelism, maximum degree of parallelism, task schedulers, cancellation tokens. But the defaults usually work well. You can start simple and optimize later if needed. Parallel loops are perfect for embarrassingly parallel problems, where iterations are independent, where no iteration depends on another's results. Data transformations, batch processing, rendering, these fit naturally. The parallel class makes utilizing modern multi-core processors straightforward. Think of the parallel class as distributing work among a team. Instead of one person doing everything sequentially, everyone works simultaneously on different parts. The work finishes faster, and no single person is overwhelmed. CPU cores are like this team, each capable, each ready to contribute. Parallel loops divide the work and let all cores participate. Rest knowing that CPU-bound work can be parallelized easily, efficiently, with minimal code changes. Fact number 36. Plink for parallel data queries. LINQ, Language Integrated Query, lets you query collections with declarative syntax. Filter, map, aggregate, express what you want, not how to get it. Plink extends this to parallel execution. Add as parallel to a query, and it runs in parallel across multiple cores. The same query that ran sequentially now uses all available cores. Filtering a large collection, transforming data, computing aggregates all happen in parallel. Speedup is often near linear with core count, especially for CPU-intensive operations. Plink handles partitioning automatically, dividing data among threads, ensuring balanced work distribution. It handles merging results back together. You focus on the query logic. Plink handles the parallel execution. There are options with degree of parallelism to limit concurrency, as ordered to preserve order with cancellation for cancellation support. But often as parallel is enough. The defaults are sensible, the performance gains are real. Plink is elegant because it extends familiar LINQ syntax. You already know how to write queries. Adding parallelism is trivial. The learning curve is gentle, the benefits are substantial. It's another example of .NET making advanced features accessible. Imagine a river flowing, and you want to examine every stone in it. Sequentially, you'd look at one stone at a time, slowly making progress. In parallel, multiple people examine different stones simultaneously. The work completes much faster. Plink is this parallel examination, leveraging multiple cores to process data faster while keeping your code simple and declarative. Let Plink handle the parallelism. Write queries naturally, and let the runtime optimize execution. Fact number 37. Hardware intrinsics for SIMD acceleration. Modern processors have SIMD instructions, single instruction, multiple data. One instruction can operate on multiple values simultaneously. Add 4 numbers in the time it takes to add one. This is powerful for certain workloads, graphics, audio, scientific computing, anywhere you process arrays of numbers. .NET exposes these hardware intrinsics directly. You can write C# code that compiles to specific SIMD instructions like AVX2 or SSE4. This gives you performance approaching handwritten assembly while staying in managed, safe C#. The system runtime intrinsics namespace provides these capabilities. Vector types, intrinsic functions, hardware detection, everything needed to leverage SIMD. And the JIT can optimize these further, knowing exactly what instructions to generate. This is advanced, specialized optimization. Most code doesn't need it, but for performance-critical hot paths, hardware intrinsics can deliver dramatic speedups 2x, 4x, 8x faster depending on the operation and hardware. And you stay in C# with type safety, with debuggability, with all the tools you know. .NET's inclusion of hardware intrinsics shows its commitment to performance. It doesn't force you into unmanaged code or assembly for maximum speed. It brings low-level capabilities into the managed world, making them accessible, safe, usable. Think of SIMD as a wide brush versus a fine-tipped pen. For coloring large areas, the wide brush is much faster. For detailed work, the pen is appropriate. SIMD instructions are that wide brush, perfect for processing arrays of data, for operations that apply uniformly across many values. When you need it, .NET provides access, letting you paint quickly while staying within the managed, safe environment. Fact number 38. Devirtualization optimizations in modern JIT. When you call a virtual method or interface method, the runtime must look up which implementation to call. This indirection has cost, a pointer dereference, a branch that might be mispredicted. For tight loops calling virtual methods frequently, this overhead adds up. Devirtualization is when the JIT compiler can determine statically which implementation will be called and replaces the virtual call with a direct call. If the JIT knows the exact type, it can skip the indirection entirely. And if the method is small, it might even inline it, eliminating the call entirely. Modern .NET's JIT is increasingly good at devirtualization. With profile-guided optimization, the JIT observes which types actually flow through code at runtime and optimizes accordingly. If 99% of calls to an interface method go to one implementation, the JIT generates a fast path for that common case. This means you can write clean, polymorphic code using interfaces and base classes without sacrificing performance. The JIT sees through the abstraction and generates efficient code. You get maintainability and performance, design elegance and speed. This is the JIT acting as a partner, understanding your code's runtime behavior and optimizing accordingly. You write high-level, abstract code. The JIT compiles low-level, concrete, efficient machine code. Both sides contribute to the final result. Let yourself appreciate how the runtime works for you. Abstractions that might seem costly are optimized away. Virtual calls that should be slow become fast. The JIT is constantly improving, learning new optimization techniques, bringing better performance without you changing a line of code. Rest knowing that writing maintainable, well-designed code doesn't preclude performance. The runtime bridges the gap. Fact number 39. Numeric performance improvements and generic math. Working with numbers is fundamental. Adding, multiplying, comparing, these operations happen billions of times in typical programs. .NET has continuously improved numeric performance, adding hardware intrinsic support, vectorization, better JIT optimizations. But there was a long-standing limitation. You couldn't write generic numeric algorithms easily. If you wanted a function to work with int, float, double, you'd need 3 separate implementations or use slower, boxed arithmetic. Generic constraints couldn't express any numeric type. Modern .NET introduced generic math interfaces. Types like int and double implement interfaces like inumber, t, iaddition operators, t. Now you can write truly generic numeric code. One implementation works for all numeric types, and the JIT specializes it for each type, generating efficient code. This enables libraries that work naturally with any numeric type. Mathematical algorithms, statistical functions, geometric computations, write once, use with any number. The code is clean, generic, yet fully optimized. Combined with SIMD support and aggressive JIT optimizations, numeric code in modern .NET is fast. Really fast. Competitive with languages traditionally used for numeric computing, while maintaining C#'s safety, expressiveness, and tooling. Think of generic math as a universal adapter. One plug fits all sockets. One algorithm works with all number types. This unification reduces duplication, reduces bugs, improves maintainability, and performance doesn't suffer. The JIT ensures each specialization runs at full speed. Trust that numeric code can be both generic and fast, both reusable and efficient. Fact number 40. String interning and efficient string handling. Strings are everywhere in applications. File paths, user input, configuration values, identifiers, strings permeate code. And strings are immutable in .NET. Once created, they never change. This immutability brings safety, simplicity, and enables optimization. String interning is one such optimization. Identical string literals in your code are stored once, not duplicated. All references to hello point to the same string object in memory. This saves memory and allows reference equality checks to work for literals. You can manually intern strings with string intern if needed. This is useful for frequently compared strings. If 2 strings are interned and equal, they're the same object and reference equality is instant. But interning has costs. Interned strings live for the application's lifetime. Use it judiciously. Modern .NET has improved string handling performance dramatically. String. Create for building strings efficiently. Span-based APIs for substring operations without allocations. UTF-8 support for working directly with UTF-8 bytes. All these reduce allocations, reduce copying, improve speed. Strings might seem simple, but enormous engineering has gone into making them fast. Searching, splitting, parsing, formatting, all heavily optimized. You write straightforward string code, and it runs efficiently thanks to years of performance work in the base libraries. Strings are like the roads in a city. Everyone uses them constantly. Optimizing them benefits every application. .NET has invested heavily here, and you reap the rewards every time you work with text. Let string handling be effortless. Trust the optimizations. Write clear code, and know the platform makes it fast. As we close this 4th segment, let these performance concepts settle gently. Async/await providing scalability. The thread pool managing concurrency. Value task optimizing hot paths. Cancellation token enabling graceful cancellation. Parallel loops utilizing all cores. Plink parallelizing queries. Hardware intrinsics accessing SIMD. Devirtualization removing indirection. Generic math unifying numerics. String optimizations accelerating text processing. These are the tools that make .NET applications fast, responsive, efficient. You don't need to understand every detail. The patterns are accessible, the defaults are good, the optimizations are automatic. Write clear code, and the platform accelerates it. Use Async for I/O, parallel for CPU-bound work, leverage modern APIs, and performance follows naturally. Rest in this knowledge. Performance is not a battle you fight alone. The runtime, the JIT, the libraries all work together, constantly optimizing, constantly improving. Your code benefits from this foundation. Sleep peacefully, knowing .NET makes fast code accessible, makes scalability achievable, makes performance a partnership between you and the platform. Now we turn our attention to the developer experience, to the tools and features that make writing .NET code pleasant, productive, and safe. Let these thoughts flow gently through your mind. Fact number 41. Base class library breadth and consistency. When you start with .NET, you're not starting from nothing. You inherit a vast base class library, thousands of classes, millions of lines of carefully crafted code. Collections, file I/O, networking, text processing, cryptography, threading, XML, JSON, the fundamentals are already there, already tested, already optimized. This breadth means you spend less time searching for third-party libraries and more time building your application. Need to parse JSON? System. Text. JSON is there. Need to make HTTP requests? HTTP client is there. Need to work with dates? Datetime and datetime offset are there. The common needs are already met. But more than breadth, there's consistency. The base class library follows patterns. Once you learn how collections work, you understand list, dictionary, hash set, they follow similar principles. Once you learn the async pattern, it applies across I/O operations. This consistency reduces cognitive load. You're not constantly learning entirely new patterns. Naming is consistent. Methods are discoverable. Documentation is thorough. The base class library feels cohesive, like it was designed holistically rather than assembled from disparate pieces. This coherence makes learning easier, makes navigation intuitive, makes development pleasant. Think of the base class library as a well-stocked workshop. When you need a tool, it's probably there, organized sensibly, ready to use. You don't waste time creating basic tools from scratch. You focus on your unique work, your specific problem, your application's purpose. The library handles the fundamentals, freeing you to concentrate on what matters. Let this foundation support you. Trust in its breadth and consistency. Fact number 42. Reflection and rich metadata. .NET assemblies don't just contain code. They contain metadata, rich, detailed information about every type, every method, every property. This metadata is accessible at runtime through reflection. You can ask an assembly what types it contains. You can ask a type what methods it has. You can call methods by name, create instances dynamically, inspect attributes. Reflection enables powerful scenarios. Serialization frameworks inspect types and figure out how to serialize them. Dependency injection containers scan assemblies and wire up dependencies automatically. Testing frameworks discover test methods by looking for attributes. Plugin systems load assemblies dynamically and invoke their functionality. This metadata-driven programming is deeply embedded in .NET culture. Frameworks rely on it. Tools use it. The runtime provides it. And because metadata is standardized, tools from different vendors can interoperate, can understand each other's assemblies, can work together seamlessly. Reflection can be slow. It's runtime type information, not compile time guarantees. But modern .NET has improved reflection performance and provided alternatives like source generators for scenarios where compile-time code generation is preferable. Reflection remains valuable for dynamic scenarios where compile-time knowledge isn't sufficient. The richness of metadata means assemblies are self-describing. You can examine a DLL and understand its contents without source code. Debuggers use metadata. Documentation generators use metadata. IDE IntelliSense uses metadata. This self-descriptive nature makes assemblies easy to work with, easy to understand, easy to integrate. Imagine a book where every chapter has a detailed table of contents, every section has annotations, every concept has cross-references. You can navigate effortlessly, understand structure quickly, find what you need easily. Reflection provides this for code. Your assemblies are richly annotated, fully explorable, completely transparent. Rest knowing that .NET code carries its documentation within itself. Fact number 43. Attributes as declarative behavior drivers. Attributes are metadata you attach to code elements. A class, a method, a property, you can annotate it with attributes. These attributes carry information, express intent, drive behavior, and they're discoverable through reflection. Attributes enable declarative programming. Instead of writing code that says how to do something, you declare what you want and a framework handles the how. Mark a method with test and the testing framework runs it. Mark a property with required and the validation framework checks it. Mark a class with serializable and serialization knows to include it. This separation of concerns is powerful. Your domain code focuses on business logic. Attributes express cross-cutting concerns, validation, serialization, authorization, caching. Frameworks read these attributes and apply appropriate behavior. Your code stays clean, focused, uncluttered. .NET provides many built-in attributes, and you can create custom ones. A custom attribute is just a class inheriting from attribute. You define it, apply it to your code, and build frameworks that react to it. This extensibility means attributes aren't just for built-in scenarios. You can create domain-specific metadata systems. Attributes make frameworks less invasive. Instead of inheriting from framework-based classes or implementing complex interfaces, you often just apply attributes. Your classes remain your own, lightly annotated rather than heavily coupled to framework infrastructure. Think of attributes as labels or tags. A box labeled fragile tells handlers to be careful. A method labeled authorize tells the framework to check permissions. These declarative markers drive behavior without cluttering the implementation. Code remains readable, intent remains clear, frameworks remain flexible. Let attributes express your intentions declaratively. Trust frameworks to respect them. Fact number 44. Expression trees and LINQ providers. When you write a LINQ query against a database, something remarkable happens. Your C# code, the where clause, the select projection, doesn't execute in .NET. It's translated into SQL and runs on the database server. How is this possible? Expression trees. An expression tree is a data structure representing code. Instead of executable code, it's a tree of nodes. This node is a method call, that node is a comparison, another node is a constant. This tree can be examined, transformed, compiled into different forms. When you write a LINQ query with iQueryable, your Lambda expressions aren't compiled into regular methods. They're compiled into expression trees. The LINQ provider entity framework, for example, walks these trees, understands the operations you're expressing, and translates them into SQL or HTTP requests, or whatever the target data source requires. This is code as data. Your queries remain strongly typed C#, checked at compile time with IntelliSense support. But they're also inspectable, translatable, executable against remote systems. You get type safety and composability while the actual execution happens somewhere else entirely. Expression trees enable other scenarios too. Mock frameworks use them to verify method calls. Mapping libraries use them to generate property copying code. Anytime you need to reason about code structure programmatically, expression trees provide the foundation. This is metaprogramming made accessible. You're not writing code that writes code as text. You're working with structured representations, with typed nodes, with safe transformations. It's powerful yet approachable, enabling advanced scenarios without sacrificing C# type safety. Imagine sheet music. The notes on the page aren't sound. They're a representation of sound that can be read, transposed, performed on different instruments. Expression trees are similar, a representation of code that can be analyzed, transformed, executed in different contexts. Let expression trees bridge your code and external systems. Trust in this abstraction. Fact number 45. Nullable reference types preventing bugs at compile time. Null reference exceptions are common, frustrating bugs. You try to use an object, but it's null, and the application crashes. For decades, this was just accepted. Reference types could be null, and you had to remember to check. Nullable reference types change this. With this feature enabled, reference types are non-nullable by default. A string variable can't be null unless you explicitly declare it a string. The compiler tracks nullability through your code flow and warns when you might dereference a null value. This isn't a runtime change. The CLR still allows null references, but the compiler helps you avoid them. It analyzes your code, sees where nulls might flow, and issues warnings. You fix these warnings, add null checks or assertions, and your code becomes safer. This feature catches bugs at compile time before they reach users. A potential crash becomes a compiler warning during development. You fix it, test it, and the bug never makes it to production. This shift-left approach, catching issues earlier in the development cycle, saves time, reduces frustration, improves quality. Adopting nullable reference types in existing codebases takes work. You enable it incrementally, fix warnings gradually, improve null handling over time. But the investment pays off. Your code becomes more robust, more explicit about null handling, more trustworthy. Think of nullable reference types as guardrails on a mountain road. They don't prevent you from driving, but they warn when you're approaching the edge. You adjust, stay safe, and continue forward confidently. The compiler becomes a safety partner, watching for null-related hazards and alerting you before accidents happen. Let nullable reference types protect you. Trust the compiler's analysis. Fact number 46. Source generators eliminating reflection and boilerplate. Reflection is powerful but has costs. It's slower than direct code. It happens at runtime, and writing boilerplate code equals methods, property change notifications, serialization logic is tedious and error-prone. Source generators solve both problems. They're compile-time code generators. They analyze your code during compilation and generate additional code automatically. This generated code is compiled alongside your code, checked by the compiler, visible in your project. For scenarios that previously used reflection serialization, for example, source generators can emit specialized code at compile time. JSON serialization that was reflection-based and slow becomes generated direct code that's fast. You still write simple data classes. The generator handles the tedious serialization logic. For boilerplate scenarios, implementing iNotify property changed, for example, source generators can emit the repetitive code automatically. You mark a field with an attribute, and the generator creates the property, the change notification, all the plumbing. Your code stays clean. The generator handles the mechanical details. Source generators are analyzers that run during compilation. They see your code, can inspect attributes and patterns, and emit new files. This generated code feels like it was written by hand. It's readable, debuggable, normal C# code. But you didn't write it. The generator did. This compile-time code generation is safer and faster than runtime reflection. It's checked by the compiler, benefits from IDE features like go-to-definition, and executes at full speed. Frameworks are increasingly adopting source generators, making libraries faster and code simpler. Imagine an assistant who handles repetitive tasks while you focus on creative work. Source generators are this assistant handling boilerplate, optimizing patterns, generating tedious code so you don't have to. Let source generators reduce your workload. Trust them to handle mechanical code generation. Fact number 47. Roslyn analyzers and IDE code fixes. The C# compiler, Roslyn, is open source and extensible. You can write analyzers, custom rules that examine code and report issues. These analyzers run in the IDE during build in CI/CD. They catch problems early, enforce coding standards, prevent bugs. Analyzers can check anything: naming conventions, security patterns, performance anti-patterns, API usage mistakes. If it can be detected by analyzing code structure, an analyzer can check it. And analyzers can provide quick fixes, one-click code transformations that correct the issue. This means code quality rules aren't just documentation. They're enforced automatically. A team establishes coding standards, writes analyzers, and everyone gets real-time feedback. Mistakes are caught immediately, consistency is maintained, quality improves. The .NET ecosystem includes many analyzer packages. Security analyzers catch vulnerabilities, Performance analyzers identify inefficient patterns. API analyzers ensure you're using libraries correctly. You install these packages, and your IDE immediately starts helping you write better code. This is the IDE as a mentor. It doesn't just highlight syntax errors. It understands patterns, suggests improvements, offers to fix problems. The feedback is immediate, the corrections are automated, the learning is continuous. You become a better developer through constant, gentle guidance. Think of analyzers as spell check and grammar check for code. Just as writing tools catch typos and suggest better phrasing, analyzers catch code issues and suggest improvements. Your code becomes cleaner, safer, more consistent, and you learn best practices through repeated, contextualized feedback. Let analyzers guide you. Trust their suggestions. Fact number 48. Source link and stepping into NuGet source. Debugging used to stop at library boundaries. You could debug your code, but NuGet package code was opaque. You saw method calls disappear into libraries and return with results, but couldn't see what happened inside. Frustrating when the bug was in a library or at the boundary between your code and the library. Source link changes this. Library authors can embed source control information in their packages. When you debug and step into library code, Visual Studio fetches the source from the repository, the exact version matching your binary, and displays it. You can set breakpoints, inspect variables, understand what's happening inside the library. This transparency is invaluable. You understand behavior more deeply. You debug issues more effectively. You learn from library implementation. The boundary between your code and library code becomes permeable, crossable, no longer a barrier. Most popular NuGet packages now support source link. Entity Framework, ASP.NET Core, JSON.NET step right into their code. See how they handle your data. Understand their decisions. This openness builds trust, facilitates learning, improves debugging. The .NET ecosystem's commitment to SourceLink reflects its open culture. Libraries aren't black boxes. They're inspectable, understandable educational resources. You can learn by reading production code, by seeing how experienced developers solve problems, by understanding patterns and techniques firsthand. Imagine a glass house where every room is visible. You can see how things work, how systems connect, how decisions are made. SourceLink provides this transparency for code. Libraries become learning opportunities. Debugging becomes comprehensive. Understanding becomes deep. Let SourceLink guide you through library code. Trust in this transparency. Fact number 49. Hot reload speeding up development. Traditional development involves a cycle. Write code, compile, run, test, discover issues, stop, write more code, compile again. This cycle takes time. Each compilation, each application restart, breaks flow, interrupts thinking. Hot reload breaks this cycle. You run your application once and it stays running. You modify code, change a method, update a UI element, fix a bug, and the changes are applied to the running application instantly. No recompilation wait. No application restart. Just immediate feedback. For web applications, you modify a page, save, and see changes in the browser immediately. For desktop apps, you adjust UI layout, and it updates in the running application. For any code, you can modify logic and see results without restarting. The feedback loop becomes nearly instantaneous. This transforms development from batch processing to interactive exploration. You try ideas quickly, see results immediately, iterate rapidly. What would have taken minutes now takes seconds. Development becomes fluid, responsive, almost conversational. Hot reload works by replacing method implementations at runtime. The runtime patches the running code with your changes. Not all changes are supported. Adding fields to classes, for example, requires restart, but many common changes work perfectly. And the system tells you when restart is needed. Think of hot reload as editing a document while it's being displayed. You type, and the display updates immediately. No need to close and reopen. No need to regenerate. Just smooth, continuous refinement. Development becomes less interrupted, more flow-focused, more enjoyable. Let hot reload accelerate your feedback. Trust in this immediacy. Fact number 50. Debugger display and debugging attributes. When debugging, you inspect objects in the debugger. The default display might not be helpful, just the type name or a generic representation. You expand properties, drill down, hunt for the information you need. This takes time and breaks concentration. Debugger display attribute lets you customize how objects appear in the debugger. Apply it to a class with a format string, and instances show exactly what you want to see. A person class might display John Doe, age 30. Instead of just person, a list might show its count and first element. The customization is yours to define. Other debugging attributes enhance the experience. Debugger browsable controls whether properties appear in the debugger. Debugger type proxy provides a custom view for complex types. Debugger hidden hides methods from stack traces. These attributes tailor the debugging experience, making it clearer, faster, more informative. Library authors use these attributes to make their types pleasant to debug. When you inspect their objects, you see meaningful information immediately. This attention to developer experience, to debuggability, reflects thoughtful API design. These are small details, but they accumulate. Better debugger displays mean faster problem identification. Clearer inspection means better understanding. Enhanced debugging attributes mean less friction, more productivity, smoother development. The experience matters, and .NET provides tools to refine it. Imagine a filing cabinet where every folder has a clear, descriptive label. You find what you need instantly. Debugger display provides this for debugging, clear labels, immediate understanding, effortless navigation. Your debugging sessions become more efficient, less frustrating, more productive. Let debugging attributes enhance your experience. Trust in these refinements. As we close this fifth segment, let these developer experience concepts settle into your thoughts. The breadth and consistency of the base class library, the power of reflection and rich metadata, the declarative elegance of attributes, the transformative capability of expression trees, the safety of nullable reference types, the efficiency of source generators, the guidance of analyzers and code fixes, the transparency of source link, the immediacy of hot reload, the clarity of debugging attributes. These features combine to make .NET development pleasant, productive, safe. You're not fighting the platform. You're supported by it. The tools anticipate your needs. The libraries provide foundations. The compiler catches mistakes. The debugger illuminates problems. Development becomes smoother, less frustrating, more focused on solving problems than wrestling with tools. Rest in this knowledge. The .NET development experience is carefully crafted, continuously refined, designed to support you. From the richness of libraries to the immediacy of hot reload, every feature serves your productivity, your understanding, your success. Sleep peacefully, knowing that .NET makes development not just possible, but genuinely enjoyable. Now we enter the realm of web development, of building services and applications that connect, communicate, and serve users across the network. Let these ideas wash over you like gentle waves. Fact number 51. ASP.NET Core as a high-performance web stack. When you need to build web applications or APIs, ASP.NET Core provides the foundation. It's fast, among the fastest web frameworks in any language. Benchmarks consistently show it handling hundreds of thousands of requests per second on standard hardware. This performance isn't accidental. It's the result of careful design, years of optimization, attention to every detail. ASP.NET Core is cross-platform, running on Windows, Linux, and Mac OS. You can develop on any system, deploy to any system. This flexibility means you choose your environment based on needs and preferences, not limitations. The framework is modular. You include only what you need. Building a simple API, you can create a lean application with minimal dependencies. Building a full MVC application with views, the components are there. This modularity keeps applications small, startup fast, resource usage low. ASP.NET Core uses modern patterns. middleware pipeline for request processing, dependency injection throughout, async by default. These patterns aren't just fashionable, they're proven, efficient, maintainable. The framework guides you toward good practices naturally, and it's constantly evolving. Each release brings performance improvements, new features, refined APIs. The community is active, the documentation is thorough, the ecosystem is rich. You're building on solid ground that continues to strengthen. Think of ASP.NET Core as a racing car's chassis, light, strong, aerodynamic, engineered for performance. Everything unnecessary has been stripped away. Everything essential has been optimized. You build your application on this foundation, and it runs fast, scales well, serves users reliably. Rest knowing your web stack is world-class. Fact number 52. Minimal APIs for lightweight services. Sometimes you need a simple API. A few endpoints, some basic logic, nothing elaborate. Traditional MVC with controllers, routing attributes, and conventions might feel heavy. Minimal APIs provide a lighter approach. With minimal APIs, you define endpoints directly in your program.cs file. One line to map a route, one lambda to handle the request. No controllers, no attributes, no ceremony. Just the essential logic expressed concisely, running efficiently. This is perfect for microservices, for cloud functions, for simple backends. The entire application can be just a few dozen lines. Startup is fast, memory usage is minimal, deployment is straightforward. You're not paying for features you don't use. But minimal APIs aren't just for tiny applications. They scale to reasonable complexity. You can organize handlers into separate files, use dependency injection, apply filters and middleware. The minimalism is optional. Use what you need, skip what you don't. Minimal APIs represent a philosophy. Simplicity when possible, complexity when necessary. Start simple. Add structure as requirements grow. Don't commit to heavy frameworks prematurely. Let your application's needs guide its architecture. Imagine a small cafe that serves excellent coffee from a simple cart versus a large restaurant with extensive infrastructure. Both are valid. Both serve customers. Minimal APIs are that cart, nimble, focused, perfect for certain scenarios. When you need more, you can always build more. But starting simple has its own elegance. Let minimal APIs give you this simplicity. Fact number 53. gRPC for binary, contract-first communication. HTTP and JSON are ubiquitous for APIs. They're text-based, human-readable, easy to debug. But they're not the most efficient. Parsing JSON has cost. Text encoding adds overhead. For internal service-to-service communication, especially at scale, there's a better way. gRPC. gRPC uses protocol buffers for serialization, binary, compact, fast to serialize and deserialize. The performance difference is significant. Messages are smaller, processing is faster, bandwidth usage is lower. For high-throughput scenarios, this matters. gRPC is contract-first. You define your service in a.proto file, messages, methods, types. This contract generates both client and server code. The types are known, the operations are defined, everything is statically typed. No runtime surprises, no mismatched expectations. And gRPC supports streaming, server streaming, client streaming, bidirectional streaming. Long-lived connections with ongoing communication. This enables real-time scenarios, continuous data flows, interactive protocols. ASP.NET Core includes built-in gRPC support. Define your services, implement methods, and they're hosted alongside your HTTP endpoints. Clients are easy to generate and use. The tooling is integrated, the experience is smooth. gRPC is for internal communication, for performance-critical paths, for when efficiency matters more than human readability. It's another tool in the toolbox, available when appropriate. Think of gRPC as a dedicated phone line versus public radio. More direct, more efficient, more suitable for certain communications. Let gRPC handle high-performance service communication. Fact number 54. Built-in dependency injection container. Dependency injection is a pattern where objects receive their dependencies rather than creating them. This makes code more testable, more flexible, more maintainable. ASP.NET Core has dependency injection built in from the start. It's not an add-on. It's fundamental. You register services in the container, their lifetimes, their implementations. Singleton for objects that live for the application's lifetime. Scoped for objects that live for a request. Transient for objects created each time they're needed. The container manages creation, manages lifetime, manages disposal. When your classes need dependencies, you declare them in constructors. The container injects them automatically. No manual wiring, no service locator pattern, no global state. Dependencies are explicit, visible, easy to understand. This enables testing. Mock implementations of dependencies can be registered instead of real ones. Your classes don't know the difference. They receive what they need through constructors, making unit testing straightforward. The built-in container is simple but sufficient for most scenarios. For advanced needs, you can replace it with third-party containers. But often, the built-in one is all you need. It's fast, it's integrated. It works seamlessly with ASP.NET Core. Dependency injection might seem abstract, but it's liberating. Your classes become simpler, focused on their purpose. Dependencies are managed centrally. Testing becomes easier. Code becomes more modular. The container handles the plumbing, letting you focus on logic. Let dependency injection manage your object lifetimes. Trust the container to provide what you need. Fact number 55. Unified configuration system across environments. Applications need configuration, connection strings, API keys, feature flags, settings that vary between development, staging, and production. Managing these across environments is challenging. Hard coding is bad. Scattering configuration files is messy. .NET's configuration system provides unity. Configuration comes from multiple sources, JSON files, environment variables, command line arguments, user secrets, Azure Key Vault, anywhere you need. These sources are layered. Later sources override earlier ones. Environment variables can override appsettings.json, for example. This means you commit appsettings.json with defaults to source control. Environment-specific settings go in appsettings. Production.json. Secrets go in environment variables or key vault. No secrets in repositories. No configuration scattered everywhere. Just a clean, layered system. Access is simple. Inject iConfiguration and read values. Or use the options pattern bind configuration sections to strongly typed classes. Your code works with typed objects rather than string keys. IntelliSense works. Refactoring works. Type safety is maintained. This unified system works the same whether you're on your laptop, in a container, or in the cloud. The abstraction is consistent. Only the sources change. Your application code remains unchanged across environments. Think of configuration as water sources feeding a single reservoir. Groundwater, rainfall, rivers, they all contribute, but you draw from one place. .NET configuration is this reservoir, unified access, multiple sources, consistent throughout your application. Let configuration flow naturally from environment to code. Trust the layered system. Fact number 56. iLogger abstraction and pluggable logging. Logging is essential for understanding application behavior, diagnosing issues, monitoring health. But tying your code to a specific logging library is problematic. Libraries change, needs evolve, and ripping out logging code is painful. .NET provides iLogger as an abstraction. Your code logs to iLogger, not to a specific implementation. The actual logging provider, console, file, application insights, Serilog, is configured separately. Your code doesn't know or care which provider is used. This decoupling is powerful. You can change logging providers without touching application code. Development might log to console. Production might log to cloud monitoring. Testing might log to memory. Same application code, different configuration. iLogger supports structured logging. Instead of string formatting, you pass message templates with named parameters. Logging providers can extract these parameters, index them, Query them. Your logs become queryable data, not just text. And logging is integrated with dependency injection. Just inject ilogger and start logging. The framework provides it. Configuration determines where logs go. Your code stays clean, focused on logging events, not managing log infrastructure. Logging is like leaving breadcrumbs through a forest. When you need to retrace your steps, they guide you back. Ilogger ensures those breadcrumbs are there, recorded consistently, available when needed. Let ilogger handle your logging. Trust the abstraction to deliver messages to appropriate destinations. Fact number 57. Health checks for cloud orchestration. In cloud environments, orchestrators like Kubernetes need to know if your application is healthy. Is it ready to receive traffic? Is it still alive or has it deadlocked? Health checks provide these answers. ASP.NET Core's health check system is simple but comprehensive. You register health checks, database connectivity, dependent service availability, disk space, memory usage, custom business health. These checks run periodically, reporting status. Endpoints expose health status. /health/ready might check if the application is fully initialized. /health/live might check if it's still responsive. Orchestrators call these endpoints, using results to route traffic or restart unhealthy instances. This integration between application and infrastructure is crucial for reliable cloud deployments. Your application declares its health. The platform respects those declarations, ensuring only healthy instances receive traffic. Unhealthy instances are replaced automatically. Health checks can be simple. Does the database connection work? Or complex, are downstream services responding within acceptable latency? You define what healthy means for your application. The infrastructure enforces it. Think of health checks as a heartbeat monitor. Continuously watches, ensuring vitality. When problems arise, intervention happens automatically. Your application communicates its state, and the infrastructure responds appropriately. Let health checks bridge your application and cloud platform. Trust them to maintain reliability. Fact number 58. Background services with I-hosted service. Not all work happens in request/response cycles. Some tasks run continuously, processing queues, updating caches, synchronizing data, cleaning up resources. Background services provide structure for these long-running tasks. I-hosted service is the interface. Implement start async to begin your background work. Implement stop async to clean up when the application shuts down. Register your service and the host manages its lifetime, starting it when the application starts, stopping it gracefully during shutdown. This is perfect for workers that need to run alongside your web application. A queue processor listening for messages. A timer that triggers periodic tasks. A cache warmer that preloads data. All these fit naturally as hosted services. The host coordinates startup and shutdown. All hosted services start before the application accepts requests. All are given time to complete when shutdown is requested. This coordination ensures graceful lifecycle management, proper cleanup, no abrupt terminations. Background services use the same dependency injection, configuration, and logging as the rest of your application. They're integrated, not isolated. They're first-class parts of your application, not afterthoughts bolted on. Imagine a stage crew working behind the scenes during a performance. They're not visible to the audience, but they're essential. Background services are this crew, handling necessary work invisibly, supporting the main application always present. Let I-hosted service structure your background work. Trust the host to manage service lifetimes. Fact number 59. Rate limiting middleware. Sometimes you need to control request rates, prevent abuse, protect resources, ensure fair usage. One client shouldn't overwhelm your service. Rate limiting provides this control. ASP.NET Core includes rate limiting middleware. Configure policies, fixed window, sliding window, token bucket, concurrency limits. Apply them globally or to specific endpoints. When limits are exceeded, requests receive 429 too many requests responses. This protection happens at the framework level. You define policies declaratively. The middleware enforces them automatically. Your application code doesn't need to track request counts or implement rate logic. It's handled consistently, efficiently, transparently. Rate limiting can be simple, 100 requests per minute per client, or sophisticated, different limits for different endpoints, different limits for authenticated versus anonymous users. The flexibility is there when needed. This is defense in depth. Even if you have external rate limiting at API gateways, having it in the application provides an additional layer. If something bypasses external limits, application-level limits still protect you. Think of rate limiting as a valve controlling water flow. Too much flow damages pipes. The valve ensures safe, controlled delivery. Rate limiting is this valve for your API, ensuring sustainable usage, protecting your service from overload. Let rate limiting middleware protect your endpoints. Trust it to enforce fair usage. Fact number 60. Timeout middleware for resilience. Requests shouldn't run forever. A database query that hangs. A downstream service that never responds. Without timeouts, threads block indefinitely, resources are exhausted, the application degrades. Timeout middleware provides a safety net. You configure maximum request duration. If a request exceeds this timeout, it's canceled. Cancellation tokens propagate through your code. Async operations respect them. The request terminates gracefully, resources are released, the thread returns to the pool. This prevents resource exhaustion. Even if something downstream is misbehaving, your application remains responsive. Problematic requests are terminated. Healthy requests continue processing. The application remains stable. Timeouts should be thoughtful. Too short and legitimate requests fail. Too long and you don't get protection. But having them is essential. They're a circuit breaker for time, preventing infinite waiting, ensuring eventual completion or cancellation. Combined with retry policies and circuit breakers, timeouts form part of a resilience strategy. Distributed systems are unreliable. Services fail, networks partition, latency spikes. Resilience patterns help you handle these realities gracefully. Think of timeouts as a safety rope with a length limit. You can explore, venture forward, but there's a boundary. If you're gone too long, you're pulled back to safety. Timeouts prevent endless waiting, ensuring your application stays responsive even when dependencies don't. Let timeout middleware protect your services. Trust it to enforce reasonable request durations. As we close this sixth segment, let these web and service concepts settle into your mind. ASP.NET Core's high performance, minimal APIs simplicity, gRPC's efficiency, dependency injections structure, unified configurations consistency, iLogger's flexibility, health checks cloud integration, background services coordination, rate limitings protection, timeout middleware's resilience. These features work together, creating a comprehensive web platform. You build services that are fast, maintainable, resilient, observable. The framework provides patterns, enforces best practices, handles infrastructure concerns. You focus on business logic, on features, on value. The platform handles the rest. Rest in this knowledge. Building web services with .NET means building on a mature, performant, thoughtfully designed stack. From the smallest microservice to the largest application, the tools are there, the patterns are proven, the performance is exceptional. Sleep peacefully, knowing ASP.NET Core provides everything needed for modern web development. Now we explore data access, networking, security, and globalization, the features that connect your applications to databases, to users worldwide, to secure communications. Let these thoughts drift through your mind like clouds across a quiet sky. Fact number 61. ADO.NET Provider Model. At the foundation of .NET Data Access lies ADO.NET, a set of classes for connecting to databases. The beauty of ADO.NET is its provider model. Common interfaces, IDB connection, IDB command, iData reader, define what database access looks like. Different providers implement these interfaces for different databases. SQL Server has a provider. PostgreSQL has a provider. MySQL, Oracle, SQLite, they all have providers. But your code can work with the common interfaces, remaining database agnostic if desired. Switch providers by changing connection strings and registration, not by rewriting data access code. This abstraction enables higher-level frameworks. Entity Framework Core sits on top of ADO.NET providers. Dapper, a lightweight ORM, uses them too. The provider model creates layers of abstraction, each building on the one below, each offering different trade-offs between control and convenience. ADO.NET itself is low-level. You write SQL directly, map results manually, manage connections explicitly. This control is valuable for performance-critical scenarios, for complex queries, for situations where ORMs don't fit. The foundation remains available, always there when you need it. Think of ADO.NET as the transmission system in a vehicle. Higher-level systems sit on top, automatic transmission, cruise control, advanced features. But underneath, the fundamental mechanism remains reliable and accessible when direct control is needed. Let ADO.NET provide the foundation for data access. Trust its provider model to support diverse databases. Fact number 62. Entity Framework Core Evolution and Performance. Entity Framework Core is .NET's primary ORM, Object Relational Mapper. It lets you work with databases using .NET objects. Define classes for your data, and Entity Framework maps them to database tables. Query using LINQ, and Entity Framework translates to SQL. Save objects, and changes are persisted automatically. Entity Framework Core has evolved dramatically. Early versions had performance limitations. Developers sometimes avoided it for hot paths. But modern Entity Framework Core is fast, competitive with handwritten ADO.NET code in many scenarios. Years of optimization, better SQL generation, improved change tracking have transformed it. The development experience is excellent. Migrations handle schema changes. Scaffolding generates code from existing databases. LINQ queries are type-safe, refactorable, expressive. You write less boilerplate, focus more on domain logic. Entity Framework Core supports multiple databases through providers. SQL Server, PostgreSQL, MySQL, SQLite, Cosmos DB, write once, target many databases. The abstraction isn't perfect, database-specific features exist, but for common scenarios, portability is real, and it continues improving. Each release brings performance enhancements, new features, better diagnostics. The team listens to community feedback, addresses pain points, pushes the framework forward. Using Entity Framework Core means riding this wave of continuous improvement. Think of Entity Framework Core as a skilled translator at a diplomatic conference. You speak in your native language, C# objects, and LINQ. The database speaks SQL. The translator facilitates communication, making it seamless, making it feel natural. You focus on your domain, and Entity Framework handles the translation. Let Entity Framework Core simplify your data access. Trust its evolution toward performance and capability. Fact number 63. Expression trees translating LINQ to SQL. We mentioned expression trees earlier, but their role in LINQ deserves deeper attention. When you write a LINQ query against Entity Framework, where clauses select projections, join operations, you're not writing executed code. You're building expression trees. Entity Framework walks these trees, understanding the operations you've composed. It translates them into SQL queries that execute on the database server. Your where clause becomes a SQL where clause. Your select becomes SQL column selection. Your ordering, grouping, joining, all translated faithfully. This translation isn't simple. SQL and LINQ don't map perfectly. Some LINQ operations have no direct SQL equivalent. Some SQL capabilities aren't expressible in LINQ. Entity Framework bridges these gaps, generating efficient SQL when possible, throwing helpful errors when translation isn't feasible. The beauty is that your queries remain C#. They're checked at compile time. IntelliSense works. Refactoring tools work. Yet they execute on the database, filtering billions of rows to return only what you need. The boundary between application and database becomes fluid. This is declarative programming at its finest. You express what data you want, not how to retrieve it. Entity framework determines the how, generating optimized SQL, leveraging database indexes, pushing computation to where data lives. Your code remains high-level while execution remains efficient. Imagine asking a librarian for books in natural language. You don't need to know the filing system, the catalog structure, the shelf organization. You express what you want, and the librarian handles the details. Expression tree translation is this: expressing queries naturally while the framework handles database mechanics. Let expression trees bridge your code and your database. Trust the translation. Fact number 64. Output caching for APIs. APIs often return the same response to repeated requests. Why regenerate the response every time? Why query the database, process data, serialize JSON repeatedly when the result doesn't change? Output caching stores responses and serves them directly on subsequent requests. ASP.NET Core's output caching middleware intercepts requests, checks if a cached response exists, and returns it if valid. Cache by route, by query parameters, by headers define what makes responses unique. Set expiration policies, time-based, tag-based, custom logic. This dramatically reduces load. Expensive operations, complex queries, heavy computation, external API calls happen once. The cached result serves hundreds or thousands of subsequent requests. Response time drops from hundreds of milliseconds to single-digit milliseconds. Output caching is also cache-aware. Very headers tell clients and proxies how to cache. E-tags enable conditional requests. The full HTTP caching model is supported, making your APIs good citizens of the web's caching infrastructure. And it's middleware, so it's configurable per endpoint. Some endpoints cache aggressively. Others don't cache at all. Some vary by user. Others serve the same response to everyone. The flexibility matches real-world needs. Think of output caching as a well-organized photocopier. The first time you need a document, someone retrieves the original and makes a copy. Subsequent requests receive copies of that copy. Instant, effortless, identical. API responses work the same way when cached. Let output caching accelerate your APIs. Trust it to serve responses efficiently. Fact number 65. Request decompression middleware. Clients often send compressed data, gzip, brotli, deflate, large JSON payloads, file uploads. Any significant data might be compressed to save bandwidth. Your application needs to decompress this data transparently. Request decompression middleware handles this automatically. It examines content encoding headers, identifies compression format, decompresses the body, and provides uncompressed content to your application. Your controllers and handlers receive normal data, unaware of compression. This is infrastructure concern handled at the framework level. Your application code doesn't deal with compression streams, doesn't check headers, doesn't manually decompress. It's transparent, automatic, reliable. The middleware supports multiple compression formats and can be extended for custom ones. Configuration determines which formats are accepted. Everything is declarative. Everything is consistent across your application. This pairs with response compression, where your responses are compressed before sending. Together, they minimize bandwidth usage in both directions, making your API efficient over slow networks, respectful of data caps, fast even when connections aren't. Imagine mail that arrives compressed and is automatically unpacked before delivery. You receive normal mail, unaware it was compressed during transit. Request decompression is this: handling compression transparently, letting your application work with normal data. Let middleware handle compression concerns. Trust it to process requests efficiently. Fact number 66. WebSocket stream and real-time improvements. Real-time communication between servers and clients is increasingly important. Chat applications, live dashboards, collaborative editing, these need bidirectional, low-latency communication. WebSockets provide this, and .NET support continues improving. WebSocket Stream is a modern addition, providing efficient streaming over WebSocket connections. It works naturally with async streams, enabling elegant patterns for real-time data. You can send and receive messages asynchronously, process them as they arrive, all with clean, readable code. The performance has improved dramatically. Modern .NET handles thousands of concurrent WebSocket connections on single servers. Memory usage is optimized. Throughput is high. Latency is low. Real-time applications can scale to substantial user counts. SignalR builds on WebSocket support, providing higher-level abstractions. It handles connection management, reconnection, fallback protocols. You write simple hub methods, and SignalR handles distribution to connected clients. Real-time becomes accessible without deep protocol knowledge. These improvements make real-time features practical for more applications. What once required specialized infrastructure now runs on standard web servers. Real-time isn't exotic anymore. It's another capability in your toolkit, ready when needed. Think of WebSockets as a dedicated phone line versus sending letters. The connection stays open, messages flow instantly in both directions, latency is minimal. Real-time communication becomes natural, immediate, interactive. Let WebSocket support enable real-time features. Trust the infrastructure to handle connections efficiently. Fact number 67. TLS 1.3 and networking upgrades. Security and performance in networking continue advancing. TLS 1.3, the latest transport layer security protocol, brings improvements in both areas. Handshakes are faster, one round trip instead of two. Security is stronger, weak algorithms are removed. Modern .NET supports TLS 1.3 fully. These networking upgrades happen at the framework level. HTTP client, Kestrel web server, SignalR, they all benefit. You don't modify code to use TLS 1.3. You just run on modern .NET, and your applications automatically use the best available protocols. Beyond TLS, HTTP/2 and HTTP/3 support continues maturing. These protocols bring multiplexing, header compression, improved performance. Again, framework support means your applications benefit without code changes. The .NET team tracks networking standards, implements them, optimizes them. As the web evolves, .NET evolves with it. Your applications stay current, stay performant, stay secure without requiring rewrites or major updates. This is infrastructure investment paying dividends. Networking is complex, security is critical, performance matters. .NET handles these concerns at the platform level, letting you focus on application logic while benefiting from continuous improvements. Imagine roads that are constantly maintained, upgraded, made safer and faster without disrupting traffic. Networking improvements in .NET are like this: continuous enhancement, better performance, stronger security, all transparent to your applications. Let .NET's networking stack handle protocols. Trust it to stay current with standards. Fact number 68. Globalization and localization APIs. Applications serve global audiences. Different languages, different cultures, different conventions for dates, numbers, currencies. Supporting this diversity is globalization. Adapting your application to specific locales is localization. .NET provides comprehensive support for both. Culture Info represents cultures, ENUS for United States English, FRFR for France French, JAJP for Japan Japanese. These cultures define formatting rules, sorting rules, calendar systems. Set the current culture and date formatting, number formatting, string comparison all adapt automatically. Datetime and datetime offset respect cultures. Numbers format with appropriate separators and decimal points. Currency symbols match the culture. Sorting follows culture-specific collation rules. This happens automatically when you use .NET's formatting and parsing APIs. The framework handles complexity, right-to-left languages, complex calendar systems, diverse number formats. You write culture-aware code once, and it adapts to different locales. The same application serves users worldwide without separate code bases. This cultural awareness extends throughout the framework. Regular expressions, string operations, data binding, culture permeates .NET's design. The platform recognizes that applications are global, that users are diverse, that one size doesn't fit all. Think of globalization support as a skilled diplomat who understands every culture's customs. They adapt their behavior appropriately, bowing in Japan, shaking hands in America, using appropriate greetings everywhere. Your application, with proper globalization, adapts similarly. Let .NET's globalization APIs handle cultural diversity. Trust them to format and parse correctly for any locale. Fact number 69. Resource files for multi-language apps. Supporting multiple languages requires translating text, UI labels, error messages, notifications. Resource files provide structure for this. You create resource files for each language containing key-value pairs. Your code references keys, and the framework retrieves values for the current culture. A resource file for English might have welcome equals welcome. The French resource file has welcome equals bienvenue. Your code asks for welcome, and users see it in their language. This separation of code and text makes translation manageable. The resource system supports fallback. If a string isn't translated for a specific culture, it falls back to a parent culture, eventually to the default. Users always see something, even if translations are incomplete. This graceful degradation prevents blank screens or missing text. Tooling supports resource files well. Visual Studio provides editors. Translation tools can import and export them. The workflow develop, extract strings, translate, import is well established. Teams have refined these processes over years of multi-language development. Modern .NET also supports JSON-based localization, providing alternatives to traditional resource files. The principle remains: separate translatable content from code, provide translations per culture, let the framework select appropriate text at runtime. Think of resource files as a phrase book with sections for each language. You look up a phrase, and the book gives you the right translation for your current language. Applications work similarly, looking up strings, receiving translations, displaying localized content. Let resource files organize your translations. Trust the framework to select correct languages. Fact number 70. Cryptography APIs and secure primitives. Security requires cryptography, hashing passwords, encrypting data, signing messages, verifying signatures. .NET provides comprehensive cryptographic APIs, implementing standard algorithms correctly, securely, efficiently. The system, security, cryptography namespace contains everything needed. SHA algorithms for hashing, ES for encryption, RSA and ECDSA for asymmetric operations, HMAC for message authentication, random number generators for cryptographic randomness. All the building blocks are there. These implementations are carefully engineered. They avoid timing attacks, handle key material securely, use platform-provided cryptographic primitives when available. Security is hard, subtle bugs lead to vulnerabilities. Using framework-provided implementations reduces risk compared to writing cryptography from scratch. Higher-level APIs simplify common scenarios. Password hashing APIs use appropriate algorithms and parameters. Data protection APIs handle key management automatically. You can secure data without becoming a cryptography expert. The cryptography story continues improving. Algorithms are updated when standards evolve. Performance improves as implementations are optimized. Security issues are patched quickly. Staying on modern .NET versions means benefiting from ongoing security improvements. Think of cryptography APIs as a bank's vault system. The mechanisms are complex, the security is critical, the expertise required is specialized. You use the vault without understanding its internal mechanisms, trusting that security professionals designed it correctly. Cryptography APIs are this vault, secure, reliable, professionally designed. Let .NET's cryptography APIs handle security. Trust the implementations to protect your data. As we close this 7th segment, let these technical concerns settle into your consciousness. ADO.NET's provider model enabling database diversity. Entity framework cores evolution toward performance and capability. Expression trees bridging LINQ and SQL. Output caching accelerating APIs. Request decompression handling compressed payloads. WebSocket improvements enabling real-time features, TLS and networking upgrades staying current with standards, globalization supporting worldwide users, resource files organizing translations, cryptography APIs providing secure primitives. These features handle complexity so you don't have to. Data access is abstracted. APIs are accelerated. Real-time is accessible. Security is handled correctly. Global reach is achievable. The platform addresses concerns that would otherwise consume development time, letting you focus on unique application features rather than infrastructure challenges. Rest in this knowledge. .NET provides solutions for common challenges: data, networking, security, globalization. You build on proven implementations, on tested patterns, on carefully engineered infrastructure. Sleep peacefully, knowing that these concerns are addressed comprehensively, that the platform supports building applications that are fast, secure, and globally accessible. Now we explore interoperability, legacy support, and how .NET bridges different worlds, connecting to native code, hosting in various environments, modernizing gradually. Let these concepts flow through your mind like a gentle breeze. Fact number 71. P/invoke and native DLL interop. Sometimes you need to call native code, existing C libraries, operating system APIs, specialized hardware interfaces. P/invoke, platform invoke, provides this bridge. You declare the function signature in C#, mark it with the DLL import attribute, and the runtime handles marshalling data between managed and unmanaged worlds. This marshalling is automatic for simple types. Integers, strings, basic structures, they convert seamlessly. For complex scenarios, you can control marshalling explicitly, specifying how data should be transformed. The flexibility accommodates virtually any native API. P/invoke lets you leverage existing native libraries without rewriting them. A legacy C library with decades of development, millions of lines of tested code, you can call it from C#. Graphics APIs, scientific computing libraries, system utilities, if they expose C interfaces, P/invoke can reach them. There are performance considerations. Crossing the managed/native boundary has cost. For hot paths called millions of times, this matters. But for most scenarios, the overhead is acceptable, and the ability to reuse native code outweighs the cost. Modern .NET continues improving P/invoke. Source generators can generate bindings automatically. Performance optimizations reduce marshalling overhead. The interop story keeps getting better, making native integration smoother. Think of P/invoke as a translator at a border crossing. Two regions speak different languages, follow different rules. The translator facilitates communication, handles conversions, makes interaction possible. P/invoke is this translator, enabling managed code to converse with native code seamlessly. Let P/invoke bridge managed and native worlds. Trust the marshalling to handle conversions. Fact number 72. COM interoperability both directions. COM, Component Object Model, is an older Windows technology for component interoperability. Many Windows APIs and applications expose COM interfaces. Office automation, DirectX, system components, COM is pervasive in Windows ecosystems. .NET provides bidirectional COM interop. You can call COM objects from .NET code. The runtime generates wrapper classes, handles reference counting, marshals method calls. From C#, COM objects look like normal .NET objects. You call methods, access properties, handle events. The COM details are hidden, and you can expose .NET objects as COM objects. Legacy VB6 applications, older COM clients, they can consume .NET components as if they were native COM. This enables gradual migration, where new functionality is written in .NET but integrated with existing COM-based systems. Interop assemblies represent COM-type libraries in .NET terms. Tools generate these automatically. Once generated, you reference them like any .NET assembly. IntelliSense works, type safety exists, yet behind the scenes, COM marshalling happens transparently. This interoperability preserved massive investments in COM-based systems. Organizations didn't need to rewrite everything immediately. They could adopt .NET gradually, integrating with existing code, modernizing at their own pace. The bridge was strong, the migration path was clear. Think of COM interop as universal power adapters. Different plugs, different voltages, but the adapter makes devices compatible. COM interop adapts between COM and .NET, making them work together despite different models. Let COM interop bridge old and new. Trust the runtime to handle protocol differences. Fact number 73. Unmanaged hosts loading the CLR. Usually, you run .NET applications by launching them directly, double-clicking an executable running from command line. But sometimes native applications need to host the CLR, loading it as a library and executing managed code within their process. This is common in extensibility scenarios. A native application wants to support plugins written in .NET. It loads the CLR, creates an app domain or assembly load context, loads the managed assembly, and calls into it. The managed code runs within the native host process, sharing its address space. Game engines use this for scripting. Native code handles rendering, physics, low-level systems, performance-critical tasks. Game logic, scripting, high-level behavior runs in managed code, benefiting from C#'s productivity, safety, and tooling. Database servers and web servers also use hosting. SQL Server can host the CLR for stored procedures. IIS hosts the CLR for ASP.NET applications. The native host provides infrastructure, and managed code provides application logic. Hosting APIs have evolved over .NET's lifetime. Modern APIs are cleaner, more flexible, supporting isolation and unloading better than previous versions. The capability remains. Native applications can embed managed runtime when beneficial. Think of CLR hosting as inviting a specialist consultant into your organization. Your team handles core operations, but for certain tasks, you bring in expertise. The consultant works alongside your team, contributing specialized knowledge. Hosted CLR is this consultant embedded within native applications, providing managed code capabilities. Let hosting APIs embed the CLR where needed. Trust the runtime to coexist with native code. Fact number 74. IIS and high-performance hosting. Internet Information Services, IIS, has been the traditional hosting platform for ASP.NET on Windows. It provides process management, HTTP handling, security integration, performance features. Billions of requests have been served through IIS over decades. Modern ASP.NET Core doesn't require IIS but integrates with it when appropriate. The Kestrel web server, built into ASP.NET Core, can run standalone or behind IIS as a reverse proxy. IIS handles SSL termination, load balancing, advanced routing. Kestrel handles application logic. This architecture provides flexibility. In development, run Kestrel directly. In production, deploy behind IIS, Jinx, or any reverse proxy. The application code remains unchanged. Only deployment configuration differs. IIS integration is mature, stable, highly optimized. Years of production usage have refined it. Enterprise features, Windows authentication, detailed logging, management tools are well developed. For Windows-based deployments, IIS remains a solid choice. But .NET's hosting story extends beyond IIS. Containers, systemd, cloud platforms, ASP.NET Core runs anywhere. The framework provides built-in web server and adapts to various hosting models. You choose what fits your infrastructure. Think of IIS as an experienced stage manager. They handle logistics, coordinate resources, ensure everything runs smoothly. The performers focus on performance while the stage manager handles infrastructure. IIS is this manager, providing hosting infrastructure so applications focus on logic. Let IIS handle hosting when appropriate. Trust its maturity and stability. Fact number 75. App domains and legacy isolation models. In older .NET framework, app domains provided isolation within a single process. Multiple app domains could exist in one process, each with separate assemblies, separate security contexts, separate configuration. This enabled scenarios like application isolation in shared hosting, plugin isolation, dynamic loading and unloading. App domains had limitations. Cross-app domain calls required marshalling, incurring performance costs. Memory wasn't truly isolated, shared heap, shared garbage collector, and complexity was significant. Managing app domain boundaries required careful design. Modern .NET Core removed app domains as a primary isolation mechanism. The one app domain per process model simplified the runtime. For true isolation, use separate processes or containers. For code loading flexibility, use assembly load context, which provides some isolation benefits without full app domain overhead. This evolution reflects changing needs. Containers provide better isolation than app domains ever could. Microservices architecture uses separate processes naturally. The heavyweight machinery of app domains became less necessary as deployment patterns evolved. But understanding app domains remains valuable for maintaining legacy applications. Millions of lines of code were written using app domains. That code continues running, continues serving users. The knowledge persists even as new development moves forward with simpler models. Think of app domains as apartments in a building. Separate spaces, shared infrastructure, some isolation but not complete. Modern approaches are separate buildings, truly isolated, independently managed. Both models serve purposes, but architectural preferences have shifted. Let assembly load context provide modern isolation. Trust simpler models for new development. Fact number 76. Dynamic code generation with reflection. Emit. Sometimes you need to generate code at runtime, not just calling methods dynamically, but creating entirely new methods, new types, new assemblies. Reflection. Emit provides this capability. You programmatically emit IL instructions, defining types and methods in memory. This is powerful for frameworks. Serializers generate specialized code for each type they encounter, avoiding reflection overhead at runtime. Proxy generators create wrapper classes dynamically. Mock frameworks emit implementation classes on demand. Dynamic language runtimes compile script code into IL at runtime. Reflection. Emit is low-level. You work with IL instructions directly. You manage stack behavior, handle branches, ensure type safety. It's complex, requiring deep understanding of IL and the runtime. But the power is immense. You can create any valid IL, implementing any logic dynamically. Modern alternatives often replace reflection. Emit. Expression trees provide higher-level, safer code generation. Source generators handle code generation at compile time. But reflection. Emit remains available for scenarios requiring maximum flexibility, runtime code creation, or compatibility with existing frameworks. The ability to generate code at runtime enables entire categories of frameworks that would otherwise be impossible or impractically slow. Dynamic languages on .NET, advanced serialization, dynamic proxies, all rely on this capability. Think of reflection. Emit as a 3D printer for code. You specify the structure programmatically, and executable code materializes. This manufacturing on demand enables flexibility impossible with precompiled code alone. Let reflection. Emit generate code when needed. Trust it for dynamic scenarios requiring ultimate flexibility. Fact number 77. Dynamic method for lightweight runtime IL. While reflection. Emit can create entire assemblies and types. Sometimes you just need a single method. Dynamic method provides this lighter weight alternative. Create a method, emit IL for its body, and execute it. No assembly creation, no type definition, just one method. Dynamic method is perfect for short-lived code generation. Create a method, use it, let it be garbage collected. The overhead is minimal, the lifetime is flexible. For scenarios needing temporary specialized code, dynamic method is ideal. Performance frameworks use dynamic method extensively. Generate optimized accessor methods for specific types. Create specialized comparison functions. Build custom conversion routines. All at runtime, all tailored to specific types and scenarios encountered. The limitation is scope. Dynamic methods are methods, not full types. They can't have fields, can't implement interfaces, can't be as richly featured as full types. But for their purpose, fast, temporary, specialized methods, they're perfect. This lightweight, dynamic code generation fills a niche. Heavy enough to be powerful, light enough to be practical. Specialized enough for performance, simple enough to use reasonably. It's another tool in the runtime's extensive toolkit. Think of dynamic method as a quick sketch versus a detailed painting. Sometimes you need a quick drawing to communicate an idea. Detailed art comes later if needed. Dynamic method is the sketch, fast, lightweight, fit for purpose. Let dynamic method create specialized methods. Trust it for temporary code generation needs. Fact number 78. Gradual modernization of legacy systems. Many .NET applications were built years ago on .NET Framework. They work, they're valuable, they're critical to business operations. But they're not on modern .NET. Migration seems daunting. Massive code bases, tight deadlines, limited resources. How do you move forward? Gradual modernization is the answer. You don't rewrite everything overnight. You migrate incrementally. Extract a service, modernize it to .NET Core, deploy it alongside the legacy application. Extract another piece, modernize it. Slowly, the system transforms. .NET Standard helped this transition. Libraries targeting .NET Standard could run on both .NET Framework and .NET Core. Shared code between old and new. This bridge enabled gradual migration, reducing the all-or-nothing pressure. Modern tooling supports this journey. Analyzers identify compatibility issues. Upgrade assistance automate parts of migration. Documentation guides common scenarios. The path is well-lit, well-traveled. Many organizations have modernized successfully, and their experiences inform the tooling. The key is breaking the problem into manageable pieces. One service at a time, one library at a time. Each piece modernized brings benefits, better performance, new capabilities, reduced technical debt. Progress compounds over time. Think of modernization as renovating a house while living in it. You don't tear everything down and rebuild. You renovate room by room, maintaining livability throughout. Legacy application modernization is similar, incremental improvement, maintaining operation, gradually transforming. Let gradual migration reduce risk. Trust the incremental approach to modernization. Fact number 79. Side-by-side deployment avoiding DLL hell. DLL hell was a nightmare in older Windows development. Shared libraries in system directories, version conflicts, applications breaking when other applications installed incompatible versions. One application's update could break another. It was fragile, frustrating, unpredictable. .NET's side-by-side deployment eliminated this. Each application can carry its own dependencies. Different versions of libraries can coexist peacefully. Application A uses library version 1.0. Application B uses version 2.0. Both live on the same machine without conflict. This isolation extends to the runtime itself. Multiple .NET versions install side by side. Applications specify which runtime they target, and the correct one loads. Upgrading the runtime for one application doesn't affect others. This model enables forward progress without breaking existing applications. New runtimes release with improved features and performance. Applications adopt them when ready, not when forced. The stability is reassuring. Your application continues working regardless of what else installs. Modern container deployments take this further. Each container has exactly the dependencies it needs, nothing shared, complete isolation. But even on traditional deployments, side-by-side support prevents the chaos of DLL hell. Think of side-by-side deployment as individual supply kits for mountain expeditions. Each team carries exactly what they need, independent of other teams. One team's choices don't affect others. Applications work the same way, self-contained, independent, isolated. Let side-by-side deployment prevent conflicts. Trust application isolation to maintain stability. Fact number 80. Enterprise-friendly versioning model. Enterprises move slowly, deliberately, cautiously. They can't chase every new version immediately. They need stability, predictability, long-term support. .NET's versioning model accommodates these needs. Long-term support releases receive updates for 3 years, security fixes, critical bug fixes, stability improvements. Organizations can standardize on LTS releases and plan upgrade cycles around their release cadence. The runway is long, the support is guaranteed. Standard term support releases are newer, faster moving with shorter support windows. For applications needing latest features, STS releases are appropriate. For stable, conservative deployments, LTS releases are better. This dual track provides choice. Innovative projects can move fast. Conservative projects can move slowly. Both are supported, both are valid, both are respected by the release model. Version numbers are clear. Major versions signal significant changes. Minor versions add features. Patch versions fix bugs. The semantic versioning makes understanding release scope easy. You know what kind of changes to expect. And compatibility guarantees protect investments. Code written for earlier versions usually runs on later versions unchanged. Breaking changes are rare, documented, necessary. Your applications age gracefully, supported by continued runtime evolution. Think of .NET versioning as a train system with express and local trains. Express trains are fast, stopping only at major stations. Local trains stop everywhere, moving carefully. Both reach destinations, both serve different needs. Choose your train based on your journey requirements. Let versioning provide stability. Trust LTS releases for enterprise needs. As we close this 8th segment, let these interoperability and legacy support concepts settle into your mind. P/invoke bridging managed and native code. COM interop connecting old and new technologies. CLR hosting enabling managed code in native applications. IS providing mature hosting infrastructure. App domains as historical isolation models. Reflection. Emit generating code dynamically. Dynamic method creating lightweight specialized methods. Gradual modernization enabling incremental progress. Side-by-side deployment preventing conflicts. Enterprise-friendly versioning supporting stable operations. These features acknowledge reality. Applications exist in complex environments. Legacy systems continue operating. Migration happens gradually. Stability matters. .NET doesn't demand you abandon existing investments. Provides bridges, compatibility layers, migration paths. You can move forward while respecting the past. Rest in this knowledge. .NET supports the messy reality of enterprise development, interoperability requirements, legacy systems, gradual modernization. The platform provides tools for these challenges, enabling progress without disruption. Sleep peacefully, knowing that .NET accommodates real-world complexity, that enterprise needs are respected, that stability and innovation can coexist. Now we explore the tools and ecosystem that surround .NET development, the command line interfaces, diagnostics, observability, and the community that binds it all together. Let these final concepts drift through your consciousness like leaves floating on a stream. Fact number 81. .NET CLI as a unified developer tool. The .NET command line interface is your gateway to the entire .NET ecosystem. One tool, countless capabilities. Create new projects with .NET New. Build with .NET Build. Run applications with .NET Run. Test with .NET Test. Publish with .NET Publish. Everything flows through this unified command. This consistency is comforting. You don't need dozens of different tools, each with unique syntax and behavior. The .NET CLI provides a coherent interface. The patterns are predictable. Once you understand the basic structure, new commands feel familiar. The CLI is also scriptable, perfect for automation. CI/CD pipelines use it extensively. Build servers, deployment scripts, development workflows, all leverage the same .NET commands developers use locally. This consistency between development and production environments reduces friction, prevents surprises, and the CLI is extensible. Custom commands can be added. Global tools integrate seamlessly. The ecosystem extends the CLI organically, adding capabilities while maintaining the unified interface. This single entry point simplifies onboarding. New developers learn one tool and gain access to the entire development workflow. The cognitive load is lower, the learning curve is gentler. Everything starts with .NET. Think of the .NET CLI as a Swiss Army knife for developers. Multiple tools in one compact package, all accessed through a consistent interface. You carry one tool but have many capabilities. Development becomes more fluid, more efficient, more enjoyable. Let the .NET CLI be your development companion. Trust its unified interface to simplify workflows. Fact number 82. Global and local .NET tools. Tools extend the .NET CLI. Some tools should be globally available, accessible from any directory, any project. Others should be project-specific, versioned with the project, ensuring consistent tooling across team members. Global tools install machine-wide. Run .NET tool install G-tool name, and it becomes available everywhere. Useful for development utilities, code formatters, deployment tools, anything you want accessible regardless of current directory. Local tools are project-specific, defined in a manifest file. Each project declares the tools and versions it needs. Team members run .NET tool restore, and they get exactly the right tools. No version mismatches, no missing dependencies. The tools travel with the project. This flexibility accommodates different needs. Personal tools can be global. Project-specific tools that need version consistency can be local. Build tools that must match project requirements are local. General utilities can be global. Choose based on the scenario. The tool ecosystem is rich. Code generators, analyzers, deployment utilities, testing frameworks. Thousands of tools extend .NET development. Some from Microsoft, many from the community. All installable through the same mechanism, all following the same patterns. Think of .NET tools as apps on your phone. Some apps you want always available. Others are specific to certain activities. Global tools are the always available ones. Local tools are context-specific, appearing when relevant. Both types enhance capability without cluttering unnecessarily. Let .NET tools extend your workflow. Trust the tool system to manage extensions cleanly. Fact number 83. One-shot tool execution for CI/CD. Sometimes you need a tool once for a single operation without installation. CI/CD pipelines particularly benefit from this, running tools without permanent installation, ensuring clean environments, avoiding tool accumulation. The .NET tool run command enables this. Specify the tool and its arguments, and it runs in an isolated environment. No global installation, no lasting footprint. Perfect for automated environments where cleanliness and repeatability matter. This pattern keeps CI/CD pipelines lean. You don't install tools globally on build servers, potentially causing conflicts or version issues. Each pipeline run uses specific tool versions, runs them temporarily, leaves no residue. The ephemeral nature also improves security. Tools run with limited scope, specific to their execution. No persistent installation means no persistent vulnerability surface. The tool exists briefly, performs its task, and disappears. This approach aligns with modern infrastructure patterns, immutable deployments, containerized builds, disposable environments. Nothing persists unnecessarily. Everything is explicit, versioned, reproducible. Think of one-shot tool execution as renting equipment for a specific job. You don't buy and store equipment you rarely need. You rent it, use it, return it. Build pipelines work similarly, borrowing tools temporarily, using them precisely, returning to clean state. Let one-shot execution keep pipelines clean. Trust temporary tool usage for automation. Fact number 84. CLI schema introspection for smart tooling. The .NET CLI isn't just for humans. Tools can introspect it, discovering available commands, understanding parameters, generating completions. This machine-readable interface enables sophisticated tooling built on top of the CLI. IDEs use this to provide command line integration. Type .NET in the terminal, and IntelliSense suggests commands. Select a command, and parameter completion guides you. The IDE understands the CLI structure because the structure is discoverable. Build tools use introspection to validate commands before execution. CI/CD tools generate correct .NET invocations. Documentation generators produce accurate command references. All because the CLI exposes its structure programmatically. This self-describing nature reduces maintenance burden. When new commands are added, tooling automatically discovers them. When parameters change, tools adapt. The ecosystem stays synchronized with the CLI through introspection rather than manual updates. It's the same principle as assemblies being self-describing through metadata. The CLI extends this to commands and parameters. Everything is discoverable, everything is machine-readable, everything supports automation. Think of CLI introspection as a detailed map of a building. You don't need to memorize everything if you have the map. Tools use introspection as their map, navigating the CLI's capabilities programmatically. Let introspection enable smart tooling. Trust the self-describing CLI to support automation. Fact number 85. Shell auto-completion support. Typing commands character by character is tedious. Remembering exact syntax is burdensome. Shell auto-completion solves this. Press tab, and the shell suggests completions. Commands, subcommands, parameters, file paths, all completed automatically. The .NET CLI supports auto-completion across shells, PowerShell, Bash, ZSH, Fish. Setup is simple, usually a one-time configuration. Once enabled, your shell becomes aware of .NET command structure. Type .NET BU and press tab. It completes to .NET build. Type .NET new and press tab. It shows available templates. Type .NET add and press tab. It suggests package, reference, and other options. The shell guides you through command construction. This reduces errors. You're less likely to mistype commands when completion guides you. You're more likely to discover features when suggestions show what's available. The feedback loop tightens, development accelerates. Auto-completion is a small feature with outsized impact. It makes the CLI friendlier, more discoverable, less intimidating. New users learn faster. Experienced users work more efficiently. Everyone benefits from this polish. Think of auto-completion as a helpful assistant standing by your side. Before you finish asking, they anticipate what you need. They offer suggestions, prevent mistakes, speed your work. Shell auto-completion is this assistant, anticipating, suggesting, guiding. Let auto-completion accelerate your command line work. Trust it to guide you toward correct commands. Fact number 86. Diagnostics tools, .NET Trace, counters, profilers. When applications misbehave, performing poorly, consuming excess memory, behaving unexpectedly, you need visibility. Diagnostics tools provide this, letting you observe runtime behavior, capture traces, analyze performance. .NET Trace captures performance traces, CPU usage, method calls, async operations, garbage collections. These traces can be analyzed in Purview or other tools, revealing performance bottlenecks, inefficient code paths, unexpected behavior. .NET Counters displays real-time performance counters, request rate, memory usage, exception count, thread pool statistics. Watch these counters while reproducing issues, correlating behavior with metrics, understanding what's happening inside your application. .NET Dump captures memory dumps for offline analysis. When applications crash or hang in production, dumps provide forensic evidence. Load them in Visual Studio or debugging tools, inspect object graphs, identify memory leaks, understand state. These tools are cross-platform, lightweight, production-safe. Use them in development to understand behavior. Use them in production to diagnose issues. The same tools work everywhere, providing consistent diagnostic capabilities. Think of diagnostics tools as medical instruments. When something's wrong, you need accurate measurement. Temperature, blood pressure, imaging. Each instrument reveals different aspects. Diagnostic tools are similar, each revealing different dimensions of application health. Let diagnostics tools illuminate runtime behavior. Trust them to reveal what's happening inside. Fact number 87. Diagnostic source and activity for tracing. Understanding request flow through distributed systems is challenging. A request enters your application, calls other services, queries databases, touches caching layers. How do you track this journey? Diagnostic Source provides instrumentation points. Code can emit diagnostic events, request started, database query executed, service called. These events carry contextual information, enabling observers to track what's happening. Activity represents a unit of work, a request, a database query, a method execution. Activities have parent-child relationships, building a tree representing work hierarchy. This structure enables distributed tracing, where requests span multiple services. Together, Diagnostic Source and Activity form the foundation for observability. They're low-level, lightweight, pervasive throughout .NET libraries. SP.NET Core, HTTP Client, Entity Framework, all emit diagnostic events through these mechanisms. This instrumentation is standardized. Different observability tools can consume the same events. You instrument once and various monitoring solutions can observe. The abstraction separates instrumentation from observation. Think of Diagnostic Source and Activity as a ship's log and navigation chart. The log records events as they happen. The chart shows the journey structure. Together, they enable understanding where you've been, how long things took, what happened along the way. Let Diagnostic Source provide observability foundation. Trust Activity to structure trace information. Fact number 88. OpenTelemetry integration. OpenTelemetry is an industry standard for observability, traces, metrics, logs. It provides vendor-neutral instrumentation, letting you switch observability backends without changing application code. .NET's OpenTelemetry integration is deep, mature, production-ready. OpenTelemetry collectors gather telemetry from applications and forward it to backends, Jaeger, Zipkin, Application Insights, Datadog, anywhere. Configure the collector and telemetry flows. The application doesn't know or care about the destination. .NET's instrumentation integrates seamlessly. ASP.NET Core automatically generates spans. HTTP client propagates trace context. Database calls are traced. You get distributed tracing with minimal configuration. The framework does the work. Custom instrumentation is straightforward. Create activities, add tags, record events. The patterns are consistent with built-in instrumentation. Your application-specific telemetry integrates naturally with framework telemetry. This standardization benefits everyone. Tool vendors support OpenTelemetry, ensuring compatibility. Developers learn one instrumentation model. Organizations can choose observability platforms without lock-in. The ecosystem grows healthier through standardization. Think of OpenTelemetry as a universal language for observability. Different tools speak different dialects, but OpenTelemetry provides common vocabulary. Everyone can communicate, everyone can understand. Observability becomes interoperable, flexible, vendor-neutral. Let OpenTelemetry provide observability standards. Trust its integration to enable comprehensive monitoring. Fact number 89. Community roadmaps and skill progression. Learning.NET is a journey. Where do you start? What do you learn next? How do you progress from beginner to expert? The .NET community provides guidance through roadmaps, learning paths, skill progressions. Community-created roadmaps visualize learning journeys. They show foundational concepts, intermediate topics, advanced specializations. They suggest order, highlight dependencies, provide direction. These roadmaps distill collective experience into accessible guides. Microsoft Learn offers structured learning paths, step-by-step modules, hands-on exercises, achievement tracking, progress from basics through specialization. Whether you're learning web development, cloud development, or game development, paths exist. The community also creates tutorials, videos, blog posts, sample projects, multiple perspectives, different teaching styles, varied approaches. You find content that resonates with your learning style, content that addresses your specific needs. This abundance of learning resources makes .NET accessible. You're not alone on your journey. Thousands have traveled similar paths, and they've left guides. The community supports newcomers, celebrates progress, encourages continuous learning. Think of community roadmaps as trails through wilderness. Experienced hikers have marked paths, placed signs, shared wisdom. You follow these trails, learning from those who've gone before. The journey becomes less daunting, more navigable, more achievable. Let community roadmaps guide your learning. Trust the collective wisdom to illuminate your path. Fact number 90. NuGet as the shared ecosystem backbone. NuGet is .NET's package manager. It's the circulatory system of the ecosystem, delivering libraries from creators to consumers. Millions of packages, billions of downloads, countless dependencies resolved. NuGet makes code sharing effortless, makes reuse natural, makes the ecosystem vibrant. Publishing packages is straightforward. Create library, package it, publish to nuget.org. Immediately, it's available worldwide. Developers discover it, use it, provide feedback. The friction between creation and consumption is minimal. Consuming packages is equally simple. Search nuget.org, find what you need, add a reference. The package and its dependencies download automatically. Updates are manageable. Versioning prevents conflicts. The system handles complexity invisibly. NuGet transformed .NET development. Before it, sharing code meant distributing DLLs manually, managing dependencies manually, updating manually. It was friction-filled. NuGet eliminated this friction. Code sharing became natural, expected, central to how development happens. The ecosystem thrives because of NuGet. Open-source libraries flourish. Commercial components distribute easily. Microsoft publishes framework extensions as NuGet packages. The entire ecosystem flows through this shared infrastructure. Think of NuGet as a global library system. Books, packages are cataloged, stored, distributed. You request a book, and it arrives. Authors publish books, and they reach readers. The system connects creators and consumers, facilitating knowledge sharing at scale. Let NuGet provide ecosystem infrastructure. Trust it to deliver packages reliably. As we close this 9th segment, let these tooling and ecosystem concepts settle into your peaceful consciousness. The .NET CLI providing unified development commands. Global and local tools extending capabilities appropriately. One-shot execution keeping environments clean. CLI introspection enabling smart tooling. Shell auto-completion guiding command entry. Diagnostics tools revealing runtime behavior. Diagnostic source and activity enabling observability. OpenTelemetry standardizing telemetry. Community roadmaps guiding learning journeys. NuGet connecting the ecosystem. These are the supporting systems, the connective tissue, the infrastructure that makes .NET development feel cohesive, supportive, community-driven. You're not developing in isolation. You're part of an ecosystem, using shared tools, consuming shared libraries, following shared patterns, contributing back. Rest in this knowledge. .NET development happens within a rich ecosystem. Tools are consistent and powerful. Learning resources abound. Packages are plentiful and accessible. The community is active and helpful. You're supported by infrastructure, by tools, by people. Sleep peacefully, knowing that .NET development is not solitary but communal, not isolated but connected, not difficult but supportive. And now we arrive at our final segment, exploring the cutting edge of .NET, machine learning, AI integration, distributed applications, modern device development, and the continuous evolution that makes .NET better with each release. Let these final thoughts complete your journey through the .NET platform as you drift toward peaceful rest. Fact number 91. ML.NET and AI integrations. Machine learning is no longer specialized, no longer separate from mainstream development. ML.NET brings machine learning into the .NET ecosystem natively. Train models, make predictions, integrate AI capabilities, all using C# and .NET tools you already know. ML.NET supports various scenarios: classification, regression, recommendation, anomaly detection, image classification. You can train custom models with your data, or use pre-trained models and fine-tune them. The library handles the complexity, exposing approachable APIs. Model training happens through declarative pipelines. You specify data sources, transformations, trainers, and ML.NET orchestrates everything. The pipeline compiles into efficient code, handling data processing and model training automatically. Integration with existing .NET applications is seamless. Models are just objects. Predictions are method calls. You don't need separate services, separate languages, separate infrastructure. Machine learning lives alongside your business logic, naturally integrated. And the ecosystem continues expanding. Integration with ONNX lets you use models trained in other frameworks. TorchSharp provides PyTorch bindings. Large language model integration enables modern AI scenarios. .NET embraces AI broadly, not narrowly. Think of ML.NET as bringing intelligence into your application's bloodstream. It's not a separate brain you consult. It's integrated capability, available everywhere, enhancing decisions naturally. Machine learning becomes another tool in your development toolkit, accessible and practical. Let ML.NET bring AI capabilities to your applications. Trust it to make machine learning accessible. Fact number 92. Tokenizers and LLM-friendly APIs. Large language models have transformed computing. ChatGPT, Claude, other models, they're powerful, but working with them requires specific handling. Text must be tokenized properly. APIs must be called correctly. Responses must be processed carefully. .NET now includes tokenizer libraries, making LLM integration straightforward. Tokenized text for various models, OpenAI, Anthropic, Llama, others. Count tokens accurately for context management. Handle encoding and decoding properly. HTTP libraries have been enhanced for streaming responses, essential for LLM interactions. Server-send events, streaming JSON parsing, efficient buffer management, everything needed for responsive AI-powered applications. The semantic kernel library provides higher-level abstractions. Define functions that models can call. Orchestrate multi-step AI workflows. Maintain conversation context. Build AI agents using familiar .NET patterns. This makes building AI-powered applications feel natural. You're not wrestling with low-level details, not managing complex state manually. The libraries handle protocol complexities, letting you focus on application logic, on user experience, on value creation. Think of LLM APIs as having a skilled interpreter for a powerful but complex oracle. The oracle has knowledge but speaks a difficult language. The interpreter makes communication smooth, natural, accessible. Tokenizers and LLM libraries are this interpreter, bridging your application and AI capabilities. Let LLM-friendly APIs simplify AI integration. Trust them to handle protocol complexities. Fact number 93. .NET Aspire and distributed app tooling. Modern applications are distributed, multiple services, databases, caches, message queues, all coordinating. Managing this complexity in development is challenging. How do you run everything locally? How do you configure connections? How do you observe behavior? .NET Aspire provides orchestration for distributed applications. Define your application's architecture, this service, that database, these message queues. Aspire handles running them locally during development, configuring connections automatically, providing observability by default. Service discovery works automatically. Services find each other without hard-coded URLs. Configuration propagates appropriately. Health checks are built in. The development experience mimics production patterns but remains approachable. Aspire isn't just for development. It generates deployment manifests for production. The same definition that runs locally produces Kubernetes configurations, container definitions, infrastructure as code. Your architecture description becomes both development and deployment specification. This reduces friction in distributed development. You're not managing dozens of terminal windows, environment variables, configuration files. Aspire orchestrates everything, letting you focus on application logic rather than development infrastructure. Think of Aspire as a conductor's score. It describes how instruments, services play together. Each musician sees their part, but the conductor ensures harmony. Aspire orchestrates your distributed applications similarly, coordinating services, ensuring they work together beautifully. Let Aspire simplify distributed development. Trust it to orchestrate complexity. Fact number 94. Aspire dashboard and telemetry improvements. Understanding distributed applications requires observability. Requests flow through multiple services. Failures cascade across boundaries. Performance bottlenecks hide in unexpected places. How do you see what's happening? The Aspire dashboard provides real-time observability during development. See all running services, their status, their logs, their metrics. Traces show request flow across service boundaries. Metrics display resource usage. Everything is visible, everything is accessible. This visibility transforms debugging. When something breaks, you see exactly where. When performance degrades, you see exactly why. The feedback loop tightens dramatically. Problems that would take hours to diagnose become obvious in minutes. The dashboard isn't production tooling, it's development tooling that reflects production patterns. You learn to think observably, to instrument properly, to design systems that reveal their behavior. These habits carry forward into production systems. Telemetry improvements extend beyond Aspire. OpenTelemetry integration is richer. Metrics are more comprehensive. Logging is more structured. The entire platform becomes more observable with each release. Think of the Aspire dashboard as a control room with windows into every part of your facility. You see what's happening everywhere, understand system behavior, diagnose issues quickly. Development becomes less about guessing and more about observing. Let the Aspire dashboard illuminate your distributed applications. Trust its visibility to accelerate debugging. Fact number 95. Cloud-native container optimizations. Containers are central to modern deployment. Small container images start faster, cost less to transfer, reduce attack surface. .NET continues optimizing for containers. Smaller images, faster startup, reduced memory footprint. Multi-stage Docker builds are streamlined. Base images are leaner. Runtime containers include only necessary components. You can build containers with just your application and essential runtime. No SDK, no build tools, no unnecessary baggage. Native AOT particularly shines in containers. Single executable, minimal dependencies, fast cold starts. For serverless scenarios where cold start matters, native AOT containers are remarkable, starting in milliseconds, consuming minimal memory. Layer caching is optimized. The SDK structures builds to maximize cache hits. Dependencies change infrequently, so they're cached. Your code changes frequently, but that's a small layer. Rebuilds are fast, deployments are efficient. Container security scanning integrates smoothly. Vulnerability detection, compliance checking, best practice validation, tools understand .NET containers, provide actionable guidance, help maintain security posture. Think of container optimization as packing luggage efficiently. Include exactly what you need, nothing more. Organize so frequently accessed items are convenient. Reduce weight without sacrificing essentials. .NET's container story is this efficient packing, lean, fast, practical. Let container optimizations reduce your footprint. Trust the streamlined images. Fact number 96. MAUI device feature expansion. .NET MAUI multi-platform app UI enables building applications for iOS, Android, macOS, and Windows from shared code. Native device features are crucial. Camera, GPS, sensors, notifications, applications need access to platform capabilities. MAUI continuously expands device feature support. Each release adds APIs for more platform features. The abstractions are consistent across platforms. You write code once and it works everywhere with platform-specific behavior handled appropriately. Community plugins extend this further. The MAUI community creates packages for features not yet in the framework. Bluetooth, NFC, advanced camera features, community plugins fill gaps, and popular ones often integrate into the framework eventually. The development experience is smooth. Hot reload works for MAUI. The IDE provides device emulators. Debugging works across platforms. You can develop on your preferred platform and deploy to all platforms. Cross-platform mobile development in .NET has matured. What started as experimental has become production-ready. Organizations build serious applications with MAUI, serving millions of users across platforms, maintaining single code bases. Think of MAUI as a universal translator for device capabilities. Each platform speaks its own language, iOS APIs, Android APIs. MAUI provides common vocabulary, translating appropriately for each platform. You speak once and all platforms understand. Let MAUI simplify cross-platform development. Trust its abstractions to handle platform differences. Fact number 97. Windows Process Group APIs. Managing processes is fundamental to many applications. Background workers, child processes, job orchestration. These scenarios require process management. Windows process groups provide better control, better isolation, better resource management. Process groups let you manage collections of processes as units. Start a group and all child processes belong to it. Terminate the group and all processes end cleanly. Resource limits apply to the group collectively. No orphan processes, no resource leaks, clean lifecycle management. This is particularly valuable for test runners, build systems, development tools, any scenario where processes spawn child processes. Without process groups, managing this hierarchy is error-prone. With process groups, it's reliable. The .NET APIs expose these capabilities cleanly. Create process groups, configure them, manage them, all through familiar .NET patterns. The complexity is hidden, the power is accessible. These improvements reflect .NET's commitment to Windows platform integration. While .NET is cross-platform, it still embraces platform-specific capabilities when they provide value. The balance is maintained, cross-platform by default, platform-specific when beneficial. Think of process groups as organizing work crews. Instead of managing each worker individually, you manage crews. Start the crew and everyone works. End the shift and everyone stops. Process groups provide this organizational structure for processes. Let process groups simplify process management. Trust them to maintain clean lifecycle control. Fact number 98. Post-quantum cryptography additions. Quantum computers threaten current cryptographic systems. Algorithms considered secure today, RSA, elliptic curve cryptography, could be broken by sufficiently powerful quantum computers. The security community is preparing by developing post-quantum algorithms resistant to quantum attacks. .NET is adding post-quantum cryptography support. Lattice-based algorithms, hash-based signatures, other quantum-resistant primitives, they're being integrated into the cryptography libraries. Applications can adopt these algorithms, future-proofing security against quantum threats. This transition happens gradually. Current algorithms remain, ensuring compatibility. New algorithms are added, enabling forward-looking applications to adopt them. Hybrid approaches combine classical and post-quantum algorithms, providing defense in depth. The cryptographic community is still standardizing post-quantum algorithms. NIST is finalizing selections. As standards solidify, .NET implementations follow. The platform tracks security evolution, adopts new standards, protects applications against emerging threats. This long-term security thinking is reassuring. .NET doesn't just address today's threats, but prepares for tomorrow's. Your applications, built on .NET, benefit from this forward-looking security work automatically. Think of post-quantum cryptography as building fortifications for future conflicts. Current defenses are strong, but threats evolve. New fortifications prepare for new weapons. Post-quantum cryptography is these new fortifications, protecting against threats that don't fully exist yet but will someday. Let post-quantum additions future-proof security. Trust .NET to evolve with cryptographic standards. Fact number 99. Continuous runtime and library optimization per release. Every .NET release brings performance improvements. Not just new features, but faster existing features. Better JIT compilation. More efficient garbage collection. Optimized library implementations. Improved LINQ performance. Faster serialization. better async overhead. These improvements are relentless. The .NET performance team measures everything, identifies bottlenecks, implements optimizations, benchmarks track progress across releases. Each version is measurably faster than the previous one. This work is mostly invisible to developers. You don't change code. You don't adopt new APIs. You just upgrade the runtime, and your application runs faster. It's free performance. No effort required, just benefits received. The optimizations are comprehensive. Low-level runtime improvements, library algorithm enhancements, JIT compiler intelligence, GC tuning. Everything is continuously refined. The platform becomes faster, more efficient, more capable with each release. Community contributions accelerate this. Performance enthusiasts submit optimizations. Issues are reported, investigated, fixed. The open source model means performance improvements come from many sources, benefiting everyone. Think of continuous optimization as a river polishing stones. Constant flow, gradual refinement, steady improvement. Each release polishes .NET a bit more, smoother, faster, better. The transformation is gradual but cumulative, remarkable over time. Let continuous optimization improve your applications. Trust that upgrades bring performance benefits. Fact number 100. Why upgrading .NET often gives free performance wins. This final fact ties together everything we've discussed. When you upgrade .NET versions, you often see immediate performance improvements without changing your code. Why does this happen? Because performance is embedded in the platform at every level. The JIT compiler improves, generating faster machine code from the same IL. Your methods run faster automatically. The garbage collector becomes more efficient, pausing less frequently, collecting more quickly. Your application's memory management improves without intervention. Library implementations are optimized. LANQ queries run faster. JSON serialization is quicker. HTTP requests complete sooner. String operations are more efficient. All the APIs you call daily become faster with each release. Runtime features are enhanced. Tiered compilation adapts better. Profile-guided optimization is smarter. Inlining is more aggressive. Devirtualization is more effective. The runtime understands your code better and optimizes more effectively. This is the platform working for you. You invest in upgrading, testing, validating, deploying. In return, you receive performance improvements, security patches, new capabilities, continued support. The investment pays dividends. And this pattern repeats with every release. .NET 7 was faster than .NET 6. .NET 8 was faster than .NET 7. .NET 9 continues this trajectory. Staying current means continuous improvement, ongoing optimization, perpetual enhancement. Think of .NET upgrades as renovating your home with self-improving materials. You install new windows, and they gradually become more energy efficient over time. You upgrade .NET, and your application becomes faster automatically. The platform evolves, and you benefit from that evolution. Let .NET upgrades bring performance improvements. Trust that staying current delivers value beyond new features. And so we've reached the end of our journey through 100 facts about .NET. We've explored the foundations, the runtime, the compilation, the memory management. We've discovered the languages, the libraries, the development tools. We've examined performance, scalability, security, and observability. We've seen how .NET bridges different worlds, supports legacy systems, and embraces modern patterns. We've witnessed continuous evolution, relentless optimization, community dedication. .NET is vast yet approachable, complex yet manageable, powerful yet accessible. It's a platform built over decades, refined through millions of applications, shaped by countless developers. It's both stable and evolving, respecting the past while embracing the future. As you drift into sleep, let these concepts settle into your subconscious. The generational garbage collector quietly cleaning, the JIT compiler optimizing, the async runtime scaling, the libraries providing functionality, the tools supporting development, the community sharing knowledge. All these pieces working together, creating a cohesive platform that supports your work, your creativity, your solutions. .NET is there for you. Whether you're building a simple tool or a complex distributed system, whether you're just starting or deeply experienced, whether you're working alone or with a team, the platform provides foundations, patterns, tools, and community. It removes obstacles, accelerates development, enables success. Rest now. Let the knowledge settle. Let the concepts integrate. When you wake, .NET will still be there, reliable, capable, continuously improving. The platform that makes building software not just possible, but genuinely enjoyable. Sleep peacefully. Dream of elegant code, of solved problems, of applications that delight users. Dream of a platform that supports you, that grows with you, that respects your time and empowers your work. Good night, sweet dreams, and may your .NET journey be filled with discovery, accomplishment, and joy.